Yeah, hi everyone, welcome back. So we have been studying about linear algebra. In linear algebra, we are studying about eigenvalues and eigenvectors. So we have been solving the problems. This is the continuation of the previous video only. So we were solving some questions. So now we will solve some 10 to 15 questions more. Okay, some more questions are there. Those questions we will solve, and then we will see the concept of diagonalization. Okay, so some more concepts we need to see. So let's solve the questions first, and then we will see some more concepts. Understandable? So let's get started. You need to find out one of the eigenvalue of this particular matrix. So from here we will make one good conclusion as well. Do you see something interesting about this matrix? If you do the addition of all the elements in a particular column, 1 plus 2 plus 5 plus 7, what will be the answer? You will be getting 15. Do the addition. 2 plus 5, 7, 7, 7, 15. Do the addition of all the elements in the column. Answer I am getting is 15. Do the addition of all the elements in rows. What is the answer I am getting? 15. Right? Also you see one more thing. What do you see? That sir, I need to find out the value of eigenvalue. So what is my procedure? This is my procedure, sir. A minus lambda I, determinant should be 0. So if I find out a minus lambda I, sir, what I will end up getting? 1 minus lambda, this will be 2, 5, 2, 5, 7. This will become 2 only. This will become 5 minus lambda, 7, 1. 5, 7, 1 minus lambda, 2. And then 7, 1, 2, 5 minus lambda. This is the scenario you will be getting, and you will be equating it to 0, right? Now let's just solve it. If we are just solving this particular determinant, what I can do is that in R1 I am applying what? R1 plus R2 plus R3 plus R4. Can I do it? Absolutely, sir. For sure you can do it. In R1 I am applying this particular transformation. So for sure I can do it. So sir, when you are doing it, what will happen is that your R1 will simply become the addition. Okay, sorry. Only R1 will be getting changed, no? So in R1 what you will be getting? In R1 all the rows I am adding. So 5 plus 2 plus 1, so it will become 15 minus lambda. This will also become 15 minus lambda. This will also become 15 minus lambda. And this will also become 15 minus lambda. And you know that row wise common I can take. 15 minus lambda common I can take. So this 15 minus lambda I can take outside, and here I will get 1, 1, 1, 1. Here I will get 1, 1, 1, 1. And this 15 minus lambda I can take outside. 15 minus lambda I can take outside. So basically this is the scenario I am getting. This is the scenario I am getting. Now this particular determinant will give me something that I don't know. This particular determinant will give me something that I don't know. So I will have 15 minus lambda here. One of the factor will be 15 minus lambda. Some other value will also come. That would be equated to 0. So you are pretty sure that when you solve this particular factor, your one of the eigenvalue will come out to be 15 only. Is that understandable to you? This matrix looked like very big, sir. This matrix is also very big, and I don't know what answer I will be getting. But if the addition of all the rows and addition of all the columns are one constant value, then that constant value will surely be one of the eigenvalues. What will be the other eigenvalues that I don't know? I need to solve it. They will not ask in the examination. Okay, this will require very tough calculations. Not very tough calculation, but some time it will take. They may ask as well, but it will be time taking, right? So, but in a quicker manner, if the examiner wants you to answer within a minute, then what he would set up? He would set up a question like that, where addition of rows and column are giving you one constant value, and that constant value will surely be one of the eigenvalue. And why is it necessary? Because we know that we are going to subtract lambda, lambda, lambda from here, and eventually what will happen is that when we add up all the rows, what we will get? We will get something outward. So that will be one of the factor for sure. So lambda equals to 15 will also be one of the eigenvalue for sure. Understandable? All good? All done? So this kind of questions are famous in PSU examination, not in GATE examination, but in some PSU examination, these kind of questions are famous, where they would set up the matrix would look very complex. Like let's just say here I would have put 2, 7, then big numbers I will put, right? Very big numbers I will put. Then what will happen? If I'm picking, if I'm putting up very big numbers, then you will not be able to solve like that. So what you need to do, you need to check the summation. And if you feel like that, sir, I am getting a constant summation, then that would be the answer. Understandable? Let's move to the next one. This is a gate PYQ only, straightforward question. 2 cross 2 matrix is there, X is unknown, eigenvalues of A are mentioned, then find out the value of X. So can I write down the characteristic equation? So characteristic equation will look like somewhat like this: lambda square minus trace plus lambda square minus omega square. Understandable? Sorry. Omega square minus omega into x, that would be equal to 0. Lambda square minus trace of A into lambda plus determinant. So sigma square minus omega x. Understandable? So now they have given the eigenvalues. What is the eigenvalue? Lambda 1 is sigma plus j omega. Lambda 2 is sigma minus j omega. What is the addition of eigenvalues? That is equal to trace. Is it fine? Yes, sir. What is the multiplication of eigenvalues? Sigma plus j omega, sigma minus j omega will be sigma square plus omega square. What that would be equivalent to? That would be equivalent to determinant. So that is equivalent to omega x. So what they are saying is that sigma square plus omega square is equals to sigma square minus omega x. So sigma will get cancelled out. X is coming out to be minus omega. That's the answer. Okay. So very simple question it was. These kind of questions you should not be looking at the solution. You should be solving on your own. Understandable? Both should be equal. So x is simply coming out to be minus omega. The matrix is given. Which one of is the eigenvalue? Basically, one of the eigenvalue is minus 2. So with respect to minus 2 eigenvalue, which of the following is an eigenvector? Okay. For this particular matrix, what all eigenvalues are there? You can see that it is an upper triangular matrix. So eigenvalues will be 3, minus 2 and 1. So with respect to minus 2, what is your eigenvector? This is what they are asking. So you can check by option, but are you going to solve it completely? Look, I can check only by one element. What I mean to say is that I need to multiply 3 minus 2, 2 with 3, 2, 1. 3 minus 2, 1. Basically, here other elements are also there. No, matrix A is having other elements as well. Matrix A is having other elements as well. But I don't care about other elements. Why is that so? Why is that so? Because, sir, if I do the multiplication 3 into 3, what I will get? 9. This will become plus 4 and this will become 2. What is the answer I am getting here? First row multiply with first column. What is the answer you are getting here? 15. 15 you are getting. So if you are getting 15 as the answer, then for getting 3 minus 2, 1. So for getting 3 here, I don't know what will be the other elements here I will be getting. I don't know what will be the other elements. I just go to know the first element. And if I need 3, I will have to take 5 common. I don't know what I will get here. But what should be the eigenvalue? Eigenvalue should be minus 2. So this option would be gone. Are you able to understand this point? I am not doing the full multiplication. Only first row multiply with first column. That's it. First row multiply with first column. So 9, 4 and 2. What we are getting? 9, 4 and 2. We are getting 15, which is not desirable. Understandable? And here minus 3. That means if minus 2 is my eigenvalue. So basically I would want the multiplication to be 6. What I am saying, if my eigenvalue is minus 2 and I am saying that this is my eigenvector, then this should be the scenario, no? Ax equals to lambda x. So the first value I would want to be 6. So if I multiply this first row with first column, I would want the value to be 6. Am I getting that value? 3 into 3 minus 9 minus 4? No, absolutely not. Go. What about 3 into 1, 3 plus minus 2 into 2, 4. 2 into 2, 2 into 3, 6. What value you are getting? 13. And here the first value is 1. That means eigenvalue is 13. This is also gone. Last option is left. What you will do? In the last option I am doing it for you here. So again, upper side 3, minus 2, 2, being multiplied with 2, 5, 0. So what answer you will get? 3 into 2, 6. 3 into 2, 6, minus 10. What answer I am getting? Minus 4 here I am getting. Here I am getting minus 4. I don't know what will be the other values, but one thing I am pretty sure that minus 2 is my eigenvalue, then inside I will be getting 2 only. So yes, I may get 250. I don't need to check others because 3 options are already gone. So this has to be the answer. And also I have checked only one element, that yes, minus 2 is the eigenvalue and 2 value I am getting here. That means yes, D could be possibly one of my answer. So here it's not that you will start finding the eigenvector directly. You can do that. You can start finding the eigenvector directly as well. Or what you could have done is that you could have checked with the options. So these kind of questions we have seen a lot of times, right? I should not even be solving these kind of problems. You should be solving it on your own. Understandable? So here 5 would come here. Basically, if you solve by this method as well, a minus lambda I into x, then also it would not be a big problem for you, right? Lambda value you will simply put minus 2. So here it will become a plus 2i equals to 0. A plus 2i multiply with x equals to 0. So from here what you will find out? You will find out the value of a plus 2i here, and then x1, x2, x3 you can find out, and you will get the answer 250. Understandable? Straightforward question. It's just that I'm telling that how to solve these kind of questions in a quicker manner. Okay, because in the examination these are very famous kind of questions. They ask these kind of questions again and again. Let's go to this one. For a matrix, what is given? A minus 3i equals to 0. This is given. So you need to find out all the eigenvalues. Sir, this information is not even required. I can find out all the eigenvalues from here only. But in a quicker manner we need to do it. So what is given? Determinant of a minus 3i equals to 0. Determinant of a minus lambda I equals to 0. When we solve it, and whatever the value of lambda we get, what they are known as? Eigenvalues. So first of all, one thing I have understood, that lambda equals to 3 is one of the eigenvalue. This is one of the eigenvalue. So one eigenvalue I have got. One thing I know, that addition of eigenvalues will be equals to the trace 2 minus 1 0. So lambda 1 plus lambda 2 is coming out to be what? Minus 2. This is the first thing I am getting. And one more thing I know. What do I know? Multiplication of eigenvalues equals to the determinant. Can I find out the determinant? Or is there any shorter method? Or can I find out the determinant? No, I will have to find out the determinant. There is no other shorter method. So let's do it with the last row. So plus minus plus. So 1 minus 12 plus 3. Then minus 2, 12 plus 6. So here I am getting minus 9. Here I am getting 36. So minus 45 I am getting. What I am getting? Minus 45. Minus 45. So lambda 1 into lambda 2 is coming out to be minus 15. So this is the scenario you are getting, and another scenario you are getting is this. All the options will be mentioned in the examination, so you can check from the options as well. But without options, if you want to think, you need to think of two numbers being multiplied, they will give you minus 15. Addition, they will give you minus 2. Think of those numbers. Can you think? Small numbers are there, minus 5 and 3, right? Minus 5 and 3. Minus 5 and 3. Because minus 5 into 3 is minus 15. Minus 5 plus 2 will be minus 2. So the eigenvalues have come out to be, these are the eigenvalues. So here one eigenvalue was already 3, then another eigenvalue came out to be again 3, and then another eigenvalue was minus 5. So these are the eigenvalues that we are getting. Minus 5, 3 and 3. So for this particular matrix, these are the eigenvalues. Understandable? Very straightforward. Let's solve this question. This is a gate PIQ only. How will you solve it? In a quicker manner. 2 cross 2 matrix, 2 of the eigenvalues are mentioned. 2 of the eigenvalues are mentioned. You know that summation of eigenvalue is 12. That should be equals to the trace of it. So check the trace. Which option is giving you trace equals to 12? So this option is giving us, this option is not giving us, this option is not giving us, this option is not giving us. There you go. Let's just say if 2 options were giving us a trace of 12, then what I would have done? I would have calculated the determinant 32. So from where I am getting 32, 36 minus 4, 32 I am getting here. Here I am not getting 32. Here also I am not getting 32. Here also I am not getting 32. Then also I could have clicked on the answer. Understandable? So this is how I could have clicked on the answer. But now, sir, if I want to solve in a conventional way, then how would I solve it? So I will have to assume the matrix. Let's just say my matrix A is nothing but A, B, C, D. 2 cross 2 matrix only, no? Now you know that concept of eigenvalue Ax equals to lambda x. So what is my A? That is, sir, A, B, C, D. What is the value of x here? Sir, eigenvector is 1, 1 with respect to eigenvalue 8. Is that clear to you? This is the eigenvector. That means A multiplied with x will give you 8 into this matrix, this column vector again. Understandable? Ax equals to lambda x we are applying. This is your v1, lambda 1, which is 8. So this is being multiplied with the matrix, you will get the same answer. So what is the answer you are getting? A plus B equals to 8, C plus D equals to 8. Then you can check the option that if one of them is matching, A plus B, C plus D equals to 8, then only one option is matching. So this was very easy question actually. You don't even need to check the option. But without checking the option, how will I solve it? That I am telling. And then vector is 1 minus 1 and eigenvalue is 4. Okay, so A minus B equals to 4 and C minus D equals to minus 4. So from here what you see? A equals to 6 I am getting, B equals to 2 you are getting. You can solve these equations, no? Equation 1, 2, 3, 4. Okay, so you can solve these equations. Then next C equals to 2 you are getting and D equals to 6 you are getting. There you go. So your matrix A is coming out to be 6, 2, 2, 6. This is how you will solve the equation and get the answer. Otherwise, you can check from the options as well. So these kind of equations are coming, then you assume the matrix and then whatever the information is given, based on that solve it and get the answer correct. Understandable? Straightforward question, right? Next one. Eigenvector of the matrix is given. We need to find out the value of A plus B. Okay. So how will you do it? You can find out the eigenvectors. Basically, you need to find out the eigenvectors to be 1A, 1B. So we can find out the eigenvectors. We know that what will be the eigenvalues? Eigenvalues are simply 1 and 2. So what will be your eigenvector with respect to eigenvalue lambda equals to 1? So what that would be, sir? A minus lambda equals to 0 I need to put. So from the diagonal element I will subtract 1. A minus lambda I into x should be equals to 0. This is our target, sir. So from here we are getting 2x2 equals to 0 and 2x1 A minus lambda I equals, basically this is what I am doing, A minus lambda I into x equals to 0. So value of lambda is 1. So A minus I am doing. So how will you subtract the identity matrix from here? Only the diagonal element will be subtracted. So 2, 1 I am getting here. Then I am simply doing the multiplication. 0 multiplied with x1. So this will become 2x1. 0 multiplied with x1. This will become x1 only. Sorry, 0 multiplied with x1 will be x1. This will become x2 equals to 0. So from here, value of x2 is coming out to be 0. And x1 is a free variable. So what is the eigen vector you are getting? The eigen vector I am getting is, this is a free variable and this value is 0. Okay, so I am pretty sure that this has to be 0. A has to be 0. What about the value of B? So eigenvector with respect to lambda equals to 2 we need to check, right? So what I will do, A minus lambda equals to 0. So A minus 2i. So from the diagonal element 2 will be subtracted. From the diagonal element 2 will be subtracted. x1 and x2. So what is the answer we are getting? 0, 0. So last row is not giving us anything. 0 into x1, 0 into x2, that is equals to 0 only. From first row only I need to find out. Minus x1, 2x2 equals to 0. Understandable? Both are, one is free variable here. So what will be your eigenvector now? x1, x2 you need to write down. So eigenvector would be nothing but, let's just say our x2 is c1 or x1 is c1. If x1 is c1, then x2 will be c1 by 2. Right? So what they have said, if x1 is 1, then x2 will be 0.5. Is that clear to you? If c1 is 1, how did we do it? A minus lambda equals to 0. This is what we are doing. What is the value of lambda here? This was the lambda equals to 1. And then we need to check with respect to lambda equals to 2. When we check with respect to lambda equals to 1, A minus lambda, that would be 1, 1 you need to subtract. 0, 0, 2, 1. Here you will get x1, x2 you need to do. So from there you go to know that x2 equals to 0. x1 could be anything. x1 is not even coming in the equation. That means x1 is a free variable. So x1 could be anything. So here the vector I can get is 1, 0, 2, 0, 3, 0, 5, 0, 7, 0, 10, 0, 19, 0, 2000, 0, anything you can get. So this is one of the eigenvector. And for the other value, a minus 2i equals to 0 I need to do. So I need to subtract 2 here. So this will be minus 1, this is 0, this is 2. So x1, x2. So what you are getting? Minus x1 plus 2x2. Understandable? So x1 is twice of x2. x1 is twice of x2. That means if it is 1, then x2 has to be 0.5. So b has to be 0.5. So from here we go to know that a is 0 and b is 0.5. That means a plus b is 0.5. This is the answer you are getting. Understandable? Let's go to the next one. Eigenvalue of a 2 cross 2 matrix is -2 and -3. You need to find out the eigenvalue of matrix B. So can you write down for matrix B? Can you write down what will be your eigenvalue? For matrix B, sir, eigenvalue will be lambda plus 1, lambda plus 1, lambda plus 3 into I, 3, and lambda plus 5. Say yes or no, right? So we just need to find out the eigenvalue. So what will be the first eigenvalue? So that will simply be, let's find corresponding to -2. I am finding corresponding to -2. So what answer I am getting? This will be -1. This will also be, this will be +1. This will be +3 inverse. So what is the answer? -1/3. And what about the second eigenvalue? You need to put -3 here. So -3 plus 1, -3 plus 3. There you go. It is 0 only, right? Why it is 0? Because this will become -2, and this will become 0, and this will become 2 inverse. Anything multiplied with 0 will be 0 only. So what are the eigenvalues you are getting? -1/3 and 0. Is that clear to you? Okay, just simply put the values here. -2 plus 1 will be -1. Then -2 plus 3, 1. So it is -1. -2 plus 5, what it will give you? 3. So -1/3. -1/3. And then -3 you put here, this will become 0. So answer is 0. So without even picking up the pen, you can solve these kind of problems. Straightforward question. What about this question? Again, it is a KPIQ. What all are the eigenvalues? Is it upper triangular matrix or lower triangular matrix? No. It is not a diagonal matrix as well. That means I will have to solve it. But let's check the options. Let's try doing it smartly with respect to the options. Right? So what the options are saying? If you look at this option, -6 plus 5j, 3 plus j, 3 minus j. Is it possible? No. Is it a real matrix? Yes, sir. Is it a real matrix? Yes, sir. That means if the eigenvalues are complex, then it has to be complex conjugate. If the eigenvalues are complex, then they have to be complex conjugate. So 3 plus j, 3 minus j you are getting, but -6 plus 5j, then another -6 minus 5j you need, which is not possible because it is a 3 cross 3 matrix only. So that means option C is cut. Next, you know that what is the trace of A? Trace of A is nothing but 3 minus 1 minus 1. 3 minus 1 minus 1, that is 1. So trace of A is 1. So you need to check those options where the trace is, where the addition of eigenvalues is giving you 1. So if I check the addition here, I am getting 1 here. Okay, so this is on the hold. Here if I check the addition, here also I am getting eigenvalue. Here also I am getting addition to be 1. And if I check this one, here the addition of eigenvalues I am getting 3 plus j plus 3 minus j plus 3. So minus j minus getting cancelled out, 9 you are getting. So this is also gone. So two options I have got, right? 3 plus j, 3 minus j, 3. That means addition of eigenvalues I should get 1, which I am not getting here. So two options I have got. Now next, what I can do? I can find out the determinant of it. What will be the determinants? Directly with respect to the last row, I can do that. Directly with respect to the last row, I can do the expansion. So I am getting 1 plus 9, right? This is 3. So 1 plus 9. So here I am getting 30. What does that mean? Multiplication of eigenvalue should give you 30. Multiplication of eigenvalues. So only two options I am left with. Multiplication of eigenvalues. 3 multiply with -1 plus 3j, multiply with -1 plus -1 minus 3j. What will be the multiplication of these two? A square plus b square. What is the value of -1 square? That will be 1. Plus what is the value of 3 square? That is 9. Multiply with 3. So what is the answer you are getting? 30. That means yes, this can be one of the possible answer. What about the other? 3 plus j, 3 plus j, multiply with 3 minus j, multiply with -5. I can directly see that multiplication would come a negative value. Why is that so? Because this will be a square plus b square. So 3 square will be 9, 1 square will be 1. So 9 plus 1, 10. Multiply with -5. So value is coming out to be -50, which is wrong. That means option B is also wrong. So what is the correct answer? Option A. So what are the eigenvalues? 3, -1 plus 3j, and -1 minus 3j. So this is how with respect to option also I can do. If let's say if this matrix was a bit complex, then solving this A minus determinant of A minus lambda I would have been a complex process, no? It would take some time. So if we want to save the time, then what we can do is that we have the trace, we have the magnitude, we have the determinant, all these things we can check, or along with that we can see that options are in the complex form. That means complex conjugate should also be the eigenvalues. So this is how we can check and we can get the answer in a quicker manner rather than solving the determinant. Okay. So in the examination they will never ask you tough calculations. They will ask that how you use your intuitions. Understandable? So this is how I get the answer. That is option A. This matrix has 3 eigenvalues, which is -3, 3 and 5. And the eigenvector corresponding to eigenvalue 5 is 1, 2 and -1. Which one of the eigenvectors of M cube is? Basically, which of these options is one of the eigenvector of M cube? Do you remember one thing? If Ax equals to lambda x, then A cube eigenvector does not change. Remain same. What does that mean is that, let's just say this is a matrix A which is having 3 eigenvalues, lambda 1, lambda 2 and lambda 3. With respect to these 3 eigenvalues, eigenvectors are v1, v2 and v3. So what about A cube? So A cube will also have eigenvalues lambda 1 cube, lambda 2 cube and lambda 3 cube, and their corresponding eigenvectors would be v1, v2 and v3. Is that clear to you? So if this is one of the eigenvector for matrix A, then for A cube as well it will be one of the eigenvector. With respect to which eigenvalue? With respect to 5 cube eigenvalue. So this is the eigenvector for matrix A, this is the eigenvector with respect to 5 eigenvalue, but for matrix A cube this will be the eigenvector with respect to 5 cube eigenvalue. But this will be surely one of the eigenvector. That means 1, 2, -1 will surely be one of the eigenvector. There you go. 1, 2, -1. Okay. 1, 2, -1 will surely be one of the eigenvector. No doubt about it. Understandable? Let's go to the next one. This is a good question. Matrix P is given and 2 of the eigenvalues are mentioned, which are 1 and 2. How many eigenvalues it will have? 3 eigenvalues it will have. Directly I can see here that P multiplied with some matrix is giving you 1, 0, -1. That means P multiplied with x is giving you 3x. What does that mean? 3 is also one of the eigenvalue. So I got to know that matrix P is having eigenvalues of 1, 2 and 3. These 3 eigenvalues it is having. Understandable? All good? What you need to find? You need to find P to the power 4, 1, -1, 0. What will be the answer you will be getting? This is what you need to find. Understandable? What you know? Eigenvalues you know. A and B value here we don't know. A, B are unknown. Right? Can we find out the value of A and B somehow? Our target is finding P to the power 4, but P to the power 4, like, will you do the multiplication? P into P into P into P into P. 4 times you will have to do the multiplication. Right? We cannot do it. Higher chances are there that for sure this could be one of the eigenvector. This could be one of the eigenvector. But with respect to which eigenvalue? This could be one of the eigenvector, but with respect to which eigenvalue? That we don't know. If we get to know that, if for P we are able to find out the eigenvectors, for matrix P, if we are able to find out the eigenvectors, then our job would be done. Why is that so? Because matrix P will have the same eigenvector as P to the power 4. So if P is having this as one of the eigenvector, what does that mean? That means P to the power 4 will also have one of the eigenvector as 1, -1, 0 only. And if we know the eigenvalues of P, then do we know the eigenvalues of P to the power 4? Absolutely, sir. The eigenvalues are 1, 2 to the power 4, 16 and 3 to the power 4 is 81. These are the eigenvalues. We just need to find out that this eigenvector is corresponding to what eigenvalue. One thing I am pretty sure, that this eigenvector is not corresponding to lambda equals to 3, because lambda equals to 3, corresponding to lambda equals to 3, we are having this eigenvector. Let's just call it V3. So corresponding to lambda equals to 3, we are having V3 as the one of the eigenvector. What does that mean? That means here only two possible answers we will get. Basically, it is p to the power 4 into x. I'm not sure whether it is eigenvector or not, but I am assuming, because if they are framing the problem like that, that means there is higher chance that it will be one of the eigenvector. So if I am saying that this is one of the eigenvector, then there are two possible chances. P to the power 4 multiplied with this vector would come out to be eigenvalue multiplied with this vector, or p to the power 4 multiplied with this vector will be coming out to be eigenvalue multiplied with this vector. So here what will be the answer? Here the answer will come out to be 1 minus 1 0, and here the answer will come out to be 16 minus 16 0. These two are my possible answers now. Is that understandable to you? So I will check the option. If one of the value, if only one of the vector is mentioned, I will click on that vector. Is that clear to you or not? I will click on that particular answer. Are you able to understand how did I think of it? This is matrix P. Two eigenvalues are mentioned. Third eigenvalue I find out from here. I know that p to the power 4 will have these eigenvalues, right? Now, with respect to eigenvalue 3, this is the eigenvector we are getting. That means here, with respect to eigenvalue 81, you will also get the same eigenvector. You will also get the same eigenvector. But you are supposed to multiply p to the power 4 with 1 minus 1 0. As of now, you don't know whether 1 minus 1 0 is an eigenvector or not, but you are thinking that it might be possible that it is an eigenvector. In the examination, how will I think? That it might be possible that it is an eigenvector. But it is the eigenvector corresponding to what eigenvalue? Sir, corresponding to 3, it cannot be the eigenvector. It could be the eigenvector corresponding to 1 or 2. Whatever the eigenvector matrix P is having, the same eigenvectors p to the power 4 will also have. So this eigenvector is there corresponding to either 1 or 16. So this eigenvector will be either multiplied with 1 or it will be multiplied with 16. So you will get two kind of answer, either 1 minus 1 0 or 16 minus 16 0. 99.99% probability is there that only one of the option will be mentioned and you will be able to get the answer. So this I told how will you solve in the examination. Is that clear to you? And again, sir, here we are not sure whether it is eigenvector or not. 99% chances are there that surely they will make it eigenvector. Okay. Otherwise, why would they ask this kind of question? But now we are supposed to find out the eigenvectors of matrix P. How we will find out? Right? We don't have the values of A and B. But we can find out the value of A and B very easily. How we can find out? Matrix P being multiplied with 1 0 minus 1 is giving you 3 0 minus 3. So how will you do the multiplication? First row multiply with this column, then second row multiply with this column, then third row multiply with this column. This is how you do the multiplication, no? Right? So basically this third row multiply with this column will give you the last minus 3. Do the multiplication. P multiply with 1 0 minus 1. So last multiplication, this row being multiplied with this column. A multiply with 1, 2 multiply with 0 will be 0, B multiply with minus 1 will be minus 1. So A minus B is actually giving you the last result, which is minus 3. So A minus B is equals to minus 3. This is one of the equation we have got. Along with that, what we can see? Along with that, we can see one more thing, that a trace of matrix P is nothing but 1 plus B, which is equals to the addition of eigenvalues lambda 1 plus lambda 2 plus lambda 3, which is 1 plus 2 plus 3. 1 plus 2 plus 3. So from here I got to know that value of B is coming out to be 5. If the value of B is coming out to be 5, that means value of A has to be 2. So value of A and B also we have find out. Is that understandable to you? Value of A is 2, value of B is coming out to be 5. Basically I multiplied this matrix with this matrix to get the result. Understandable? Okay. Now I am almost pretty sure that this will be eigenvector, no? And now I know the matrix P as well. What I mean to say is that I know the matrix P. Matrix P is 0 minus 2 minus 3, then minus 1 1 minus 1 and 2 2 5. Now if they have framed the question, then I am pretty sure, not I am pretty sure, I am almost sure that 1 minus 1 should be one of the eigenvector. Now what you are left with, that if you are having matrix P, someone would say that find out all the eigenvectors. Find out the eigenvectors v1, v2, v3. And then check if this is the eigenvector. If this is the eigenvector, then it is the eigenvector corresponding to what? Corresponding to 1 or 2. That you check. But I am pretty sure, no, I am not pretty sure, I am almost sure that this will be one of the eigenvector of matrix P. So what do I do is that I multiply this matrix P with this eigenvector, which is mentioned as 1 minus 1 0. I multiply this with 1 minus 1 0. Let's see what is the result we are getting. Is this eigenvector or not? So let's see what result we get. So this multiply with 0, here you will get 2 and 0. Then you will get minus 1 and 0. So minus 2. Then you get 2 minus 2. There you go. So yes, it is the eigenvector corresponding to eigenvalue lambda equals to 2. Right? Corresponding to eigenvalue lambda equals to 2. So this was the eigenvector V2 corresponding to lambda equals to 2. Right? So for P to the power 4 eigenvector corresponding to 2 to the power 4 will be V2 only, right? And what is 2 to the power 4? That is 16. So what does that mean? That means P to the power 4 being multiplied with V2 will give you 16 into V2. So what is P to the power 4? P to the power 4 is P2. P to the power 4 is P to the power 4 only. What is V2? V2 is 1 minus 1 0. Multiply with 16, 1 minus 1 0. So what is the answer you are getting? 16 minus 16 and 0. That's the answer you will get. There you go. 16 minus 16 0. Most probably, if you are just solving the question in the examination hall, then this option will not even be mentioned. Only this option would be mentioned. So you will eradicate that, sir, one of these two possible are one of these are my possible answer. Okay. Either this will be my possible answer or this is my possible answer. Then you will check the option, you will see that this is not even mentioned. Then you will directly click on this. And what if both are mentioned? Then you will have to think, okay, 1, 2, 3, these are my eigenvalues. Then I will have to find out the matrix P. So for finding out the matrix P, I need the value of A and B. Then, sir, I am assuming that yes, this could be one of the possible eigenvectors. I need to find out the eigenvalue corresponding to it. So I find out the eigenvalue corresponding to it. Then 2 to the power 4 simply multiply by 16, you will get the answer. Very good question, but smartly you need to solve in the examination hall. Otherwise, you will never be able to solve these kind of problems. Okay, very good question. And yeah, I hope you have understood. Okay, let's go to the next one. If A is a matrix with eigenvalue lambda and corresponding eigenvector x, then for matrix e to the power A, matrix e to the power A, which all options are correct? This is what they are asking. So how e to the power A could be written? I hope you know. 1 plus a square by 2 factorial. In basics we have seen it, right? A cube divided by 3 factorial, a to the power 4 divided by 4 factorial, and so on, right? So what will be the corresponding eigenvalue? 1. Corresponding eigenvalue lambda. Corresponding eigenvalue lambda to the power 2. Corresponding eigenvalue lambda to the power 3, and so on. So what this will become? E to the power lambda. So for e to the, if matrix A is having a eigenvalue of lambda, then e to the power A is having eigenvalue of e to the power lambda. Understandable? Okay, so one of the eigenvalue is e to the power lambda, and the corresponding eigenvector will not change. That will be x only. Understandable? Corresponding eigenvector will be x only. Is that clear to you? If A is having, here you know, here only you can tell. Basically, if A is having an eigenvalue of lambda and eigenvector of x, then A square will have an eigenvalue of lambda square and eigenvector of x only. And A to the power n will have the eigenvalue of lambda n and eigenvector of x only. So eigenvector is not changing. No, this is having eigenvector of x, eigenvector of x, eigenvector of x, eigenvector of x. So all of them are having eigenvector of x only. Understandable? An identity matrix will surely have the eigenvector of x. Why is that so? Because anything multiplied with identity matrix will give you the same matrix only. This is your identity matrix. I multiply this vector x, I will get the same vector x only with the eigenvalue 1. So this is also having eigenvector x, eigenvector x, eigenvector x. So what eigenvector you will have? X only. So yes, eigenvector will be, one of the eigenvector will be x only. So both of the statements are true. There you go. Okay, understandable? What about this question? Let A be a matrix. Let A be a matrix with the given set of eigenvectors which of the following statements are true. The eigenspace of e to the power a sin a cos a square a cube a to the power minus 1 whenever defined are same as those a. Basically, eigenspace means they are simply telling that all the set of eigenvectors, are same for e to the power a. Yes. What is the expansion of e to the power a? 1 plus a square by 2 and so on. Okay. What is the expansion of sin a? It is a minus a cube by 3 factorial by 5 factorial and so on, right? And what is for cos a? 1 plus, here plus sign would come or positive sign or negative sign? Sign a, negative sign only would come, and so on. These are the factors. So you can directly sense here what you can sense, that what will be the eigenvalues here? 1 plus lambda square divided by 2 factorial and so on. So again here the eigenvalue will become lambda e to the power lambda with the eigenvector of x. Here what will be the scenario? Lambda minus lambda cube by 3 plus lambda 5 by 5 factorial and so on. So it will become sin lambda, right? And here 1 plus lambda square by 2 lambda to the power 4 and so on. This will become cos lambda, and eigenvector will remain same because all of them are having the same eigenvectors. So yes, they will have the same eigenvector, and for sure about these guys you already know they will have the same eigenvectors. But is that correct? The eigenspace of a to the power, the eigenspace of a transpose are same as those of a. That is wrong, right? If a is having eigenvalue of lambda and eigenspace and eigenvector of x, then a transpose will have the eigenvalue of lambda only, but eigenvector you cannot comment. So eigenvector would be some y. This I already told you, right? So this is wrong. So both are correct. None of the above are correct. All are wrong. Only option A is correct. Understandable? All good? So for A transpose this is not true. For A it is true, but for A transpose no. Basically for A square, A cube, e to the power a, sin a, cos a, ln I plus a, for all of them it is true. But A transpose is a different thing. You cannot expand it like that. Understandable? And for A transpose we have proven as well. No, I show you a very small proof in the last lecture, right? Ax equals to lambda x, then you take the transpose, it will become x transpose A transpose, then lambda into x transpose, then A transpose being multiplied with x transpose. If this was the scenario, no, x transpose, A transpose being multiplied with the x transpose is giving you lambda into x transpose, then you would have said that yes sir, x transpose is my one of the eigenvector. But the scenario is different now, x transpose into A transpose, so you cannot even comment what is your eigenvector. Understandable? But eigenvalue you can comment. How you can comment about the eigenvalue? You can comment about the eigenvalue because sir, if I am taking the determinant of A minus lambda I, if I take the transpose, the determinant will not change. So this is how you can comment on the eigenvalue. The eigenvalue will remain same, but eigenvector would be different. Understandable? If eigenvalue of matrix are this, then what is the eigenvalues of A transpose? Sir, that would be simply 1, 4, 3 only. So what will be the determinant of A transpose? Determinant of A transpose would be simply 1 multiplied with 4 multiplied with 3, that will be 12. Or you can say that sir, determinant of A and A transpose are always same. This I already know. Determinant of A and A transpose are always same, so that would be 1 multiplied with 3 with 1 multiplied with 4 with 3, that will be 12 only, right? Eigenvalues of A are mentioned. You need to find out the trace. So let's just say we treat this matrix as B, which is 4, which is A cube plus 4A square. A cube plus 4A square. So what will be its eigenvalues? Eigenvalues you write down. With respect to 1, it will be 1 cube plus 4. With respect to 2, it will be 2 cube 8 and 16. And with respect to minus 1, it will be minus 1 plus 4. So value will come out to be 5, 24 and 3. So these are its eigenvalues. What will be the trace? Trace of B will simply be the addition of all of them. 32. That's the answer. Is that clear to you? Absolutely very simple question, right? Eigenvalues are mentioned. In this question, eigenvalues are mentioned, then determinant of A transpose. Here, all those things I should not be solving. You should be solving on your own, right? A, and here it will be 5, 2 cube 8, 16, 24, and here minus 1 plus 4, that would be 3. So this is the answer. Trace you need to find out. Simply do the addition. Yeah, this is a good question. Think about it. I guess this is the last. Yes. Then we will study about diagonalization. So think about this question. It is a MSQ. MSQ. Which of them is a possible answer? Nullity of A is represented by 3. What does that mean? What do you mean by nullity of A? Nullity of A would represent a geometric multiplicity of lambda equals to 0. That is equals to 3. That means at least 3 eigenvectors, 3 independent eigenvectors you are having with respect to lambda equals to 0. I told you one thing, AM is always greater than or equals to GM. That means arithmetic multiplicity of lambda equals to 0 will be greater than or equals to 3. That means minimum 3 0 eigenvalues you will have. Minimum 3. That means here this is wrong, this is wrong. Minimum 3 0 eigenvalues you will have. Minimum 3. And the trace has to be 5. That means summation of all the eigenvalues has to be 5. Summation of all the eigenvalues is 5. Summation of all the eigenvalues is 5. Minimum 3 eigenvalues, 3 0 eigenvalues you need to have. Minimum 3. Lambda 4 might be 0, might not be 0, but they are for sure. So 4 0 eigenvalues also I can have, but making sure one thing, the trace has to be 5. Yes, trace is 4 plus 1, 5. Trace is 5. So option A and B both are correct. Both are possible. Both are possible. But these are not possible. Why is that so? Because minimum 0 eigenvalue I will have is 3. Minimum 0 eigenvalue I will have 3. Why is that so? Because I am having 3 independent eigenvectors. If I am having 3 independent eigenvectors, that means for sure there are 3 0 eigenvalues. So 3 0 eigenvalue has to be there. It could be 4 as well. It could be 3 as well. Alright, okay, and it cannot be 5. Why it cannot be 5? Because addition of all of them should be equals to 5 only, no? So here I cannot get all 5 0 eigenvalues. Understandable? Let's see the concept of diagonalization. Not very important. It is not very important, but who knows, in the examination it can be asked. Okay, so when you will say that matrix is diagonalizable, when you will say that a matrix is diagonalizable, so if it is a n cross n matrix, then it should have n independent eigenvectors. N independent eigenvectors. So what all are the eigenvalues here? Eigenvalues are 1, 2, 3. All are different. All eigenvalues are different. So you are pretty sure that I am having 3 independent eigenvectors for sure. That means yes, this is diagonalizable. What all are the eigenvalues here? So eigenvalues are 0, 0, 0. These are the eigenvalues, right? All 3 eigenvalues are same. It is an upper triangular matrix, no? It is an upper triangular matrix. Eigenvalues are 0, 0, 0. Right? Now what I need to comment on? I need to comment on geometric multiplicity of lambda equals to 0. Why is that so? Because I will get to know that how many independent eigenvectors I am having. How many independent eigenvectors I am having. Right? So what is the geometric multiplicity of lambda equals to 0? That is equals to nullity of A. And is it in the row echelon form? Yes sir, it is in the row echelon form. So what will be the nullity of A? If it is in the row echelon form, then what is its rank? The 2 non-zero rows are there. Rank is 3. Sorry, what is rank? Rank is 2. And what is the number of columns? 3. 3 minus 2. Nullity is 1. What does that mean? Only one independent eigenvector I can have. Only one independent eigenvector. What I will write down? Only one independent eigenvector. Only one independent eigenvector. So these kind of questions are very famous. What they would do, they will set up 4 options and they will ask you which of them is diagonalizable, which of them is not diagonalizable. So sir, 3 eigenvalues I am having here. It is a 3 cross 3 matrix, but only one independent eigenvector I am getting, not diagonalizable. Understandable? Here what all are the eigenvalues? 1, 2, 2. So here I will get one independent eigenvector for sure. I don't need to care about it, but here I need to care about it. So what I need to find out? Nullity of A minus lambda I, that is A minus 2i. So I need to find out the nullity of A minus 2i. So what I will get? 1, 0, 0. A minus 2i I am calculating. So this will actually become, you need to subtract 2, 2, 2. So this will become minus 1, this will become 0, and this will also become 0. So all these will become 0. So what is the nullity you are getting? Nullity here you are getting is, sir, number of columns 3 and non-zero row is 1. So nullity of A minus 2i you are getting is 2. What does that mean? You are having 2 independent eigenvectors. 2 independent eigenvectors. So total, here 1 independent eigenvector, here 2 independent eigenvectors. So total 3 independent eigenvectors I am getting. eigenvectors I am getting, that means yes, it is diagonalizable. So I am saying some statement, let me know whether it is true or false. If eigenvalues are repeated, then matrix will not be diagonalizable. Is that correct? If eigenvalues are repeated, then matrix will not be diagonalizable. Is it correct? No. Even if the eigenvalues are repeated, it doesn't matter. If it is giving you two independent eigenvectors, that means yes, it is diagonalizable. Second statement, if eigenvalues are different, if all the eigenvalues are different, then matrix is surely diagonalizable. Yes sir, it is correct. If all the eigenvalues are different, then matrix is surely diagonalizable. Third statement, if eigenvalues are same, then matrix may be diagonalizable. If eigenvalues are same, then matrix may be diagonalizable. Is that correct? Yes, it may be diagonalizable, it may not be diagonalizable. Understandable? So you understood everything, that how will you find out whether a matrix is diagonalizable or not. Okay, this is a very tough name. Diagonalizable. Try speaking it. Diagonalizable. Yeah. So, sir, what is the meaning of diagonalizable? I am not going to tell you. Okay. Otherwise, it will take 5 to 6 hours only to understand the meaning of diagonalization. Okay. It will take so much of time, and again, it is very less important. Very less important. In the previous year, if you would have seen, combined 3 or 4 question would have come. Combined 3 or 4. That also I am telling too much. Without even knowing the concept of diagonalization, you would have solved those problems. Okay. So it is not that important. That's why I am not going to give you the complete meaning of all those things. Understandable? So we will solve it in a manner that just we are able to solve the problems of the examination. That's it. So you need to find out the diagonal matrix of matrix A. So this is a matrix A. You need to find out its diagonal matrix, which is known as matrix B. So we are going to find out matrix B, which is that diagonal matrix of matrix A. Diagonal matrix of matrix A. Okay, that we need to find out. So what we need to do, what is the procedure? Then we will get the final answer, and then I will tell you that yeah, this is the meaning of diagonal matrix. Okay, so what is the procedure? First you find out the eigenvalues of A. So pause the video and do it on your own. Find out the eigenvalues of A. Okay, pause the video and do it on your own. What did you find out? These are the eigenvalues. Eigenvalues came out to be 2, 2, 4. Okay, now you need to find out the eigenvector corresponding to each eigenvalue. First of all, you need to think whether it is diagonalizable or not. Whether this matrix is diagonalizable or not. So for checking diagonalizable or not, we will have to find out the eigenvalue, and then we will have to find out the eigenvectors as well corresponding to eigenvalues. So I am finding out the eigenvector corresponding to lambda equals to 2. So how will I find out? A minus lambda I multiply with x should be equals to 0. So A minus 2i A minus 2i 2 yes, multiply with x should be equals to 0. And I can directly sense here nullity is coming out to be 2. Nullity will be 2. So yes, it will give us two independent eigenvectors. So yes, let's try doing it. X1 plus x2 equals to 0, and next equation is also x1 plus x2 equals to 0. Next equation is also giving us x1 plus x2 equals to 0. So x3 is a free variable. X3 is free, and let's just say x1 is minus c. X1 is minus c. So what will be x2? X2 will be x1 is minus c or c. Let me see the solution, and then I will say what I have taken. So I have taken minus 1 1 0. Okay, minus 1 1 0 0 0 1 1 0. Okay, so x1 I am taking as minus c, x2 I am taking as c, and x3 I can take anything random. So x3 is also free variable. No, x3 is also free variable, right? So let's call this as c1 and x3 as c2. So x3 I am taking as c2. X3 is c2. So this is what I have taken. So this is the solution of the equation. You are comfortable enough in finding the solution. So this is the solution. So what will be the solution vector? So the solution vector that you will get, x1, x2, x3, that you will get is minus c1, c1 and c2. So I can write down this as minus 1 1 0 0 0 1. Okay, so this is our solution vector. So two independent eigenvector I am having. Let's call this eigenvector as v1 and let's call this eigenvector as v2. So v1 and v2, two independent eigenvectors I am having. Minus 1 1 0 0 0 1. These are the two independent eigenvectors I am having. Understandable? So what was the scenario? Matrix A was given, you find out the eigenvalue, then you find out the eigenvector corresponding to lambda equals to 2. So when you find out the eigenvector, these are the eigenvectors you are getting. Two independent eigenvectors I am having, minus 1 1 0 0 0 1. This much calculation you can do on your own. Then I will find out the eigenvector corresponding to lambda equals to 4. So how will I get the eigenvector corresponding to lambda equals to 4? So a minus 4i multiply with x equals to 0. Minus 1 minus 1 minus 2. This is 1. Okay, so here also you can see that nullity will come out to be 1 only, and you can check the eigenvector as well. So what answer I will get? Minus x1 plus x2 equals to 0, x1 minus x2 equals to 0, and minus 2x3 equals to 0. So from here I am sure that x3 equals to 0, and from here I am getting that x1 equals to x2. Okay, so let's take this as C1. So what is the solution vector we are getting? x1, x2, x3. So solution vector we are getting is C1, C1 and 0. So C1 I can take common, and 1, 1, 0. Okay, so this is our third eigenvector v3. So three eigenvectors we are getting: v1, v2, v3, v1, v2 and v3. Now we will make, so what is the procedure? Matrix A was given, we find out the eigenvalues. With respect to all the eigenvalues, we have find out the eigenvectors. With respect to all eigenvalues, we have find out the eigenvectors. v1, v2, v3. Now we will make a matrix P whose columns are, what I am doing, I am making a matrix P whose columns are v1, v2 and v3. There you go. So whose columns are minus 1, 1, 0. Sir, you are just telling the procedure, you are not telling the meaning. Yes, I am only telling the procedure. We are studying linear algebra right from beginning. It's been roughly around 30 hours. For every single thing I have given the reasoning, right? But if I am not giving reasoning for one particular topic, that means there is a reason behind it. It will take so much of time, it will be very complex, and it will not be important for your examination. That's why. And then 1, 1, 0. There you go. So what is the order we have set up? v1, v2 and v3. Do you remember the eigenvalues? With respect to v1, the eigenvalue was lambda equals to 2. With respect to v2, the eigenvalue was lambda equals to 2. And with respect to v3, the eigenvalue was lambda equals to 4. So this is the setup we have made. Minus 1, 1, 0. So matrix P we have made v1, v2, v3. Now from here we will find out P inverse. Can you do it on your own? Do it on your own. Find out P inverse. What that would be? First find out the adjoint matrix and then divide by its determinant. So find out P inverse. Then you find out your diagonal matrix. What will be your diagonal matrix? Then your diagonal matrix B will be nothing but P inverse multiply with A multiply with P. This will be your diagonal matrix. Okay, so this is the P inverse, then multiply with matrix A and multiply with P. So first I multiply both of them. Okay, this is the result I am getting. Then I multiply it with this one. So those two I multiplied, and this is the result I am getting. So this diagonal matrix is surely a diagonal matrix. Basically, you are finding out the diagonal matrix of A. That means it will be a diagonal matrix. No? So it is a diagonal matrix with diagonal elements as eigenvalue of, with diagonal elements as eigenvalue of A. Say yes or no? So when we find out this matrix P inverse AP, I got to know that here the diagonal elements that I am getting, they are nothing but the lambda equals to 2, lambda equals to 2 and lambda equals to 4. Now the second doubt would be that, sir, how would I get to know that first 2 would be written, then another 2 would be written, then another 4 would be written? How would I get to know that? You would be getting to know, how would you get to know? Based on your matrix P. What was your matrix P? Matrix P was V1, V2, V3. So if it was V1, V2, V3, then you would know that First, here lambda equals to 2 would come, here also lambda equals to 2 would come, and here also lambda equals to 2 would come. If your matrix was in this manner, if P was V2, V3, V1. So can you let me know what will be your diagonal matrix B? Sir, the diagonal matrix B would come out to be in this manner. V2. Corresponding to V2, what was our eigenvalue? Corresponding to V2, our eigenvalue was 2. So 2, 0, 0. Corresponding to V3, what was our eigenvalue? Corresponding to V3, our eigenvalue was 4. And corresponding to V1, what was the eigenvalue? Corresponding to V1, eigenvalue was 2. There you go. This would have been your diagonal matrix B. Again, the diagonal element would have been the eigenvalues of A only. Diagonal matrix with the diagonal elements of eigenvalues of A. What are the eigenvalues of matrix B? What I am asking, tell me the eigenvalues of matrix B. Isn't that equal to eigenvalues of matrix A? So when you find out the diagonal matrix, the eigenvalues will not change. Eigenvalues will remain the same. When you find out the diagonal matrix, the eigenvalue remains the same. 2 to 4 here, here also 2 to 4, here also 2 to 4. So eigenvalue remains the same. How will you get to know that, sir, which eigenvalue will come first, which eigenvalue will come later on, based on your matrix P? So matrix P, if I have taken in V1, V2, V3 form, that means V1 was corresponding to lambda equals to 2, lambda equals to 2, lambda equals to 4. So 2 to 4. If I have taken V2, V3, V1 form, lambda equals to 2, lambda equals to 4, lambda equals to 2. So 2, 4, 2. Eigenvalues will remain the same. And the diagonal elements will be the eigenvalues only. That's it. How will you find out? First, take the matrix, find out the eigenvalues, find out the eigenvectors, place them, make a matrix P, then find out P inverse AP. That's it. This is the conclusion of diagonalization. So what we have done, we have studied diagonalization. I guess now there are questions only. Yes, it's like a question only. So what is given? Matrix A is given and matrix B is the diagonal matrix. So what B square will be equivalent to? You need to find out what B square will be equivalent to. So if A is the given matrix, then B is the diagonal matrix. So what is B? B is nothing but P inverse AP, right? What will be your B square? This is what they are asking. So what will be the B square? B square simply means, sir, B into B. Or I can write down, sir, P inverse AP multiply with P inverse AP, right? So what we are getting? P inverse A P into P inverse A P. So what this will give you? P into P inverse will give you I. So what we are getting? P inverse A I multiply with any matrix will give you I only, A P. What this will give you? A into A. A into A is nothing but A square. So what is the answer you are getting? B square is coming out to be P inverse A square P. So similarly, what conclusion is there, that if a matrix B is equals to P inverse AP, then B square is equals to P inverse A square P and B to the power n will be equals to P square A to the power n P. Understandable? Okay. Now if matrix B is written, can you find out the matrix A? If matrix B is given, which is P inverse AP, can you find out matrix A? Yes, sir. Pre-multiplication of P I will do. Pre-multiplication of P. Pre-multiplication of P. What it will give me? P into P inverse will give me I. So it is giving me AP. Right? So what I got? Pre-multiplication of P is giving me AP. Now post-multiplication of P inverse I will do. Post-multiplication of P inverse. Post-multiplication. Here it was pre-multiplication. Pre-multiplication of P. Now what I am doing? Post-multiplication of P inverse. P inverse. What I will be getting? Post-multiplication of P inverse. So here also P inverse will be multiplied. PB P inverse and here also AP P inverse. P into P inverse will be I. So what you are getting? A is coming out to be nothing but PB P inverse. This is your matrix A. So if matrix B is given, can you write down matrix A? For sure, sir, I can write down matrix A. Now, this was the scenario. Matrix B was given P inverse AP Again it is complete mathematics, there is nothing, okay, which come out to be PB P inverse. Can you find out the value of A square? Try finding out the value of A square. Basically, if A square, from here only if I find out the value of A square, what that will come out to be? PB square P inverse, no? From here only. Forget about A square. A square, you consider A square as a separate matrix, matrix C, and B square as a separate matrix, matrix D. Then what will happen? This P inverse will come here, it will become P, pre-multiplication. First you will do the pre-multiplication and then you will do the post-multiplication. So from here only you can understand that A square will be P inverse. Or what you can do, A square you find out, A into A. What will be your A into A? That will be, sir, PB P inverse and then PB P inverse. So this will become I. So P, B into B will become B square and P inverse. P, B square, P inverse. Very simple thing, you should be doing it on your own. And then I will get A to the power n. What will be my A to the power n? P, B to the power n, P inverse. So do I need to remember anything? Absolutely not. Only thing you need to remember is that if A is my matrix, then what will be my diagonal matrix? That's the only thing you need to remember. If A is the given matrix and B is the diagonal matrix, then B equals to P inverse AP. That's it. This is the only thing you need to remember. And A and B are known to be similar matrices. Okay. First we studied about equal matrix in the basics. Equal matrix was A equals to B. Then we studied about equivalent matrix. What was equivalent matrix? After row echelon form, what is the matrix you get? What was equal matrix? A equals to B was equal matrix, right? What was the meaning of equivalent matrix? Equivalent. Sir, there was this matrix A given. I applied some row echelon operation. R2 equals to R2 is R2 will be changed to R2 minus R1. Then whatever the matrix that I got, that was known as that was known to be equivalent. And now what is the meaning of a similar matrix? Here A and B are known to be similar matrices. Okay, what they are known to be? Similar matrices. That means if A is a given matrix and B is the diagonal matrix, then A and B are known to be similar matrices. What I will write down? Where I will write down? A and B. This I don't need to write down, right? A and B are known to be similar matrices. Similar matrices. Say yes or no. Okay, understandable? Yes. Let's solve these questions. Question A, question B, question C, and question D. All are similar kind of problem. You need to find out the answer on your own. I will surely give the solution, but try doing it on your own. Matrix A is given, lambda is the eigenvalue corresponding to eigenvector x. The P be an invertible matrix, B is defined in this manner. You need to find out the corresponding eigenvalue and corresponding eigenvector of a matrix B in terms of lambda, x and P. Will you be able to do it on your own? I will take a break, drink some water, and I will come back and we will solve these 4 problems. Okay, these are the most important 4 problems, and then we will see this question, and that's it. And one more question, and yeah, that's it. Then this topic will be completed. So here diagonalization will be completed. So 1 question, 2, 3, 4, 5, 6. 6 problems we need to solve, and after that diagonalization will be completed. Okay, and from these 6 problems only question will be asked in the examination. Nothing else will be asked. So let me take a break and then I will come back. Yeah, welcome back. So did you try this question? What is given? Ax equals to lambda x is given. That means with respect to matrix A, we are having eigenvalue lambda and the corresponding eigenvector is x. This is what is given. We need to find out the eigenvalue and eigenvector for P inverse AP. So this particular thing is given. Here I need to make P inverse AP form. So how will I be able to make P inverse AP form? How will I be able to make? So what I need to do is that I will multiply with, or what I can sense that if this is your B is P inverse AP, then can you write down the value of A? Yes sir, A is nothing but P inverse. Say yes or no. You need to comment on B, no? You need to comment on B. So let's replace A with P inverse. P inverse. Say yes or no. Why is that so? Because sir, A is nothing but P inverse. And why did I replace it? Because I need some relation in matrix B. Now I don't need P and P inverse, so I will erase them. What I will do? I will do the pre-multiplication with P inverse. pre-multiplication with pre-multiplication with P inverse. So what I will get? Lambda is a constant value, so P inverse x. So if you look closely, there is a matrix B which is being multiplied with P inverse x. You are getting P inverse x only multiply with some factor lambda. So what does that mean? If matrix A was having eigenvalue of lambda and corresponding eigenvector x, then matrix P inverse AP is having eigenvalue of lambda only but eigenvector of P inverse x. Is that clear to you? Okay, say yes or no. Do you need to mug it up? Absolutely not. You will derive it in the examination. If they are asking this kind of question, then you will derive it in this manner, that sir, I need the value of I need something regarding matrix B. So what I did, I find out matrix A, then simply put it here, then multiply and then get the answer. So this is the conclusion that I have made. Okay, no need to mug it up, but it's just that you can remember it. Let's do this scenario. This time it is PAP inverse. PAP inverse. Again the same scenario. Ax equals to lambda x is given. Right? Can I write down matrix B? What will be matrix B? So it will be P inverse BP will be equals to A. What I will do? First I will do the pre-multiplication of P inverse. So P inverse B will be PAP inverse. Then I will do the post-multiplication of P. So it will become P inverse BP. P inverse BP. So this will become A. So what is A? A is nothing but P inverse BP will be equals to lambda into x. Right? Now what I will do? I will do the pre-multiplication of P. Pre-multiplication of P. So if I do the pre-multiplication of P, what I will be getting? PBX Px. Again you can sense, if matrix B is being multiplied with Px, then you are getting Px matrix again with the constant value lambda. What does that mean? If there was a matrix A which was having eigenvalue of lambda and eigenvector of x, then there is a matrix PAP inverse will have an eigenvalue of lambda and eigenvector of Px. Okay, again nothing you need to mug up, you can derive any day in the examination. Say yes or no. If I ask you the same question for, अरे क्या हो गया भाई? Is this the same problem? Same question is there, no? Right? Next question. Here I wanted to make a to the power n, right? Otherwise, the question will not make any sense. A to the power n. Basically, B is given as P a to the power n P inverse. Otherwise, the question would be same, right? We don't want the same question. We want to frame something different. So P is given as a to the power n. B is given as P a inverse. Sorry, P a to the power n P inverse. This is your matrix B is given. So basically, any kind of relation could be given. What you will do? First, you will write down Ax equals to lambda x. Now, sir, this A I need to replace. From whatever the relation that is given, what I got to know is that a to the power n could be written as P inverse B P inverse. A to the power n could be written as P inverse B P inverse. Can you let me know if matrix A is having eigenvalue of lambda and eigenvector of x, then a to the power n will have eigenvalue of lambda to the power n and eigenvector of x. So can I write down a to the power n x would be equals to lambda to the power n x? Say yes or no. Now what is the value of a to the power n? A to the power n is nothing but P inverse B Px. That would be lambda to the power n x. Then what I will do? Pre-multiplication with P. So pre-multiplication with P if I do, then lambda to the power n is a constant value Px. So what I can sense here? Lambda to the power n Px. What does that mean? If A is having an eigenvalue of lambda and eigenvector of x, then matrix B, which is P a to the power n P inverse, will have eigenvalue of lambda to the power n and eigenvector of Px. Nothing you need to mug up. All these things you will be able to derive in the examination. Is that clear to you or not? So what will be the eigenvalue? Lambda to the power n, and what will be the eigenvector? Px. Is that clear to you? What about this question? P inverse a to the power n P. So what will be my matrix B? Yes, this is different. So what will be my matrix a to the power n? From here, a to the power n relation is coming out to be P B P inverse. What is given? Ax equals to lambda x is given. What do I know? A to the power n will be equals to lambda to the power n x. What is A to the power n? P inverse x is equals to lambda to the power n. Now multiply with P inverse, pre-multiplication of P inverse, what you will get? P inverse x. What you can sense here? B multiply with P inverse x is giving you lambda to the power n P inverse x. Okay, so matrix A is having an eigenvalue of lambda and eigenvector of x. Then the matrix B, which is defined as P inverse A to the power n P, is given as the eigenvalue of lambda and eigenvector of P inverse x. So if any good question they want to ask in the examination from diagonal matrix, then this is what they will ask. Is there any concept of diagonal matrix here? No, there is no concept of diagonal matrix. Simply the question is given, you are using your brain that sir, how I can find out the value of A to the power n, then here I can put the value and then I will get the relation that B multiplied with the matrix, you are getting some eigenvalue multiplied with another matrix. From there I am able to find out. So no concept is used, nothing new here, everything you already know and you are able to solve the question. So do you need to mug it up? Absolutely not. Okay, A is having eigenvalue of lambda and eigenvector of x. So you can make the conclusion, but again we are not writing down the conclusion in one page, because if we write down you will mug it up. So we don't need to mug it up, we can solve it in the examination hall. Let's go to the next question. This is the question that is given. Try solving it on your own. Again MSQ. Okay, length of vector A is given. Okay, length of vector A is given. The matrix B is defined, which is A into A transpose. Which of the following statements are true? Matrix B is surely diagonalizable. Can you say so? What is B? B is A into A transpose. Right? What is matrix A? Matrix A is 2027 into 1. What will be A transpose? 1 into 2027. So what will be A into A transpose? That will be 2027 into 2027. Right? But can you let me know this thing, that rank of A would always be equals to rank of A into A transpose. Do you remember this thing? And what will be the rank of A? Can you let me know the rank? The rank could be only 1. Why is that so? Because it is a non-zero column vector and minimum value could be, maximum value of rank could be 1 and minimum value could be 0. If it was a all zero vector, then the rank would have been 0. But if it is not a all zero vector, then rank would be 1 only. So here the rank is 1. That means rank of A into A transpose is 1. What does that mean? What will be the nullity? Nullity of A into A transpose is number of columns minus 1. What will be the nullity? Rank is only 1. That means only this row will be non-zero. Rest all rows will be 0, 0, 0. Rest all rows will be 0, 0, 0. So can you comment on the eigenvalues of B? Can you comment on the eigenvalues of B? Eigenvalues. Sir, nullity of B is given. Nullity of B is given as 2026. What this will represent? This will represent that B will at least have 2026 zero eigen values. Say yes or no? So if I talk about the eigenvalues of B, then how many total eigenvalues it will have? Because what is the order? Order is 2027 cross 2027. So total eigenvalues it will have will be, total eigenvalues it will have will be 0, 0, 0, 0 and some one more eigenvalue. So total it will have 2027 eigenvalues. 2027 eigenvalues. Total it will have 2027 eigenvalues. Out of them at least 2026 will be 0. Out of them at least 2026 eigenvalues will be 0. Now one eigenvalue could be 0 as well, or it could be non-zero as well. It could be either 0 or non-zero. It could be either 0 or non-zero. Now what will be that eigenvalue? That we need to think. Can you comment on the trace of B? What will be the trace of B? So trace of B will be nothing but trace of A into A transpose. And do you remember what trace of A into A transpose represent? It represents the length of A square. Do you remember this? A into A transpose. A into A transpose we need to do, no? So this is A. What will be A transpose? AB. Do the multiplication. A square, AB, AB, and B square. What is the trace here? Trace is A square plus B. Isn't it the length of A? This, if this was the matrix A, isn't it the length of A? Length of A square, because what was the length of A? Length of A was nothing but under root A square plus B square, right? So this is what the trace would represent. And what trace would represent? Trace would represent the addition of all the eigenvalues. Addition of all the eigenvalues. I am pretty sure that these eigenvalues are 0. These eigenvalues are 0. So what will be your 2027th eigenvalue? That will simply represent the magnitude of A square. And what is magnitude of A? That is 2. So your 2027th eigenvalue will be nothing but 4. There you go. So which all option? Is it diagonalizable? Is it diagonalizable? We will check that. Rank of B is 1. Yes. The only non-zero eigenvalue is 4. Yes. This is wrong. Is it diagonalizable? So what all eigenvalues we are having? For matrix B, what all eigenvalues we are having? Sir, 0, 0 and 0 and 2027. Sorry. And 4. So this will give you one independent eigenvector. And what is the order here? 2027 into 2027. This will give you one independent eigenvector. Now you know that nullity of B is 2026. Nullity of B is nothing but 2026. What does that mean? That means geometric multiplicity of lambda equals to 0 is what? 2026. Because what does the nullity of B would represent? Nullity of B would represent the geometric multiplicity of lambda equals to 0. And what is the meaning? Number of independent eigenvectors corresponding to lambda equals to 0. So corresponding to lambda equals to 0, I am getting 2026 linearly independent eigenvectors. 2026 linearly independent eigenvectors. What does that mean? Total, I am having 2027 linearly independent eigenvectors. What does that mean? It is diagonalizable. A very good question, but if your concepts are clear, then you will be able to solve these kind of problems for sure. It is diagonalizable. So matrix A was given, the length was given, A transpose we could think, A into A transpose we could think. Can we comment on the rank? Yes. If we comment on the rank, then can we comment on the nullity? Yes. Nullity if we know, then geometric multiplicity also we know. Along with that, we also know that what trace of B would represent. Trace of B would represent the length square. So one non-zero eigenvalue has to be there. One non-zero eigenvalue has to be there, and that non-zero eigenvalue will be 4. And now we know the geometric multiplicity. That means we are getting 2026 linearly independent eigenvector. From here we are getting one linearly independent eigenvectors. So total 2027 linearly independent eigenvectors we will get. So A, B, C will be correct. A very good question. Hardly one student out of 100 students would be able to think of this question in the examination hall. I don't know whether he will get it correct or not, but rest of the people will not even be able to think. So these are good quality problems. Okay. Let's go to the next one. Here as well, no concept of diagonalization is used. Only one concept is used, that if the rank is 7, then are we having, if rank is n, then are we having n linearly independent eigenvectors? If yes, then it is diagonalizable, otherwise it is not. Let's solve this question. Matrix A is given, linearly independent. Matrix B is defined. Find the sum of the absolute values of elements, sum of all the absolute values of the elements of matrix B. Okay. So what is B? B is nothing but diagonal matrix of A. And how it will look like? It will look like in this manner. It will have eigenvalue, it will have eigenvalue, and it will have eigenvalue. This is your B. I am talking about diagonal matrix of A, which is your matrix B. This is not your matrix A. I am talking about diagonal matrix of A, which is matrix B. So matrix B will look somewhat like this. What is lambda 1, lambda 2, lambda 3 here? Lambda 1, lambda 2, lambda 3 are the eigenvalues of A, where lambda 1 and lambda 2, lambda 3 are the eigenvalues of A. Is that correct? Right? Because this is the form. So what they are asking, sum of the absolute values of all the elements of matrix B. What is the meaning of absolute value? Absolute value means magnitude. Magnitude. If they have just asked the find out the sum of all the elements of matrix B, then what we would have done? Sum of all the elements of matrix B, that would have been lambda 1 plus lambda 2 plus lambda 3. What that would have been equivalent to? That would have been equivalent to trace of A. Then sir, answer would have been 3 2 plus 3 minus 5, the answer would have been 0, but this answer is wrong. This is wrong. Okay, this is wrong. Why is that so? We are talking about the absolute value. So what is our answer? Our answer is magnitude of lambda 1, magnitude of lambda 2, and magnitude of lambda 3. This is the answer. Okay, so we need to find out the eigenvalues of A, find out its eigenvalues, and then take their magnitude and get the answer. So what will be its eigenvalues? So you can find out its eigenvalue. I am doing the calculation on my own. You will do it on your own. I am not teaching you now. Okay, it is more than enough. 3 into 2, 3 plus 2, 5, 3 into 2, 6, minus 1. Complex eigenvalue we will get. Is that so? B square minus B plus minus B square minus 4AC upon 2A. Yes, so these are the eigenvalues we are getting. So eigenvalues are 5 plus under root 5 divided by 2, 5 minus under root 5 divided by 2. Someone would think that, sir, how did you do it? Basically, I know that 5 minus lambda I need to do, here minus lambda I need to do, here minus lambda I need to do. Then minus 5 minus lambda will give me one of the eigenvalue, that is lambda equals to minus 5. And then they will give me some eigenvalue. So it's like a 2 cross 2 matrix only, no? This much portion is like a 2 cross 2 matrix only. Basically, what you will do is that 2 minus lambda multiply with 3 minus lambda minus 1 into 1. So isn't it like a 2 cross 2 matrix only? And what is the characteristic equation of a 2 cross 2 matrix? Lambda square minus trace of A plus the determinant, which is 3 into 2, 6, 6 minus 1, 5. So from here I will get two eigenvalues, and one of the eigenvalue is minus 5. So minus 5, and one of the eigenvalue is minus 5. So this is how I got the eigenvalue. Okay, in a quicker manner, this is how I did it. Are you able to understand this point? Whatever the method that is suitable for you, you should apply that method only. So from here you will get one of the eigenvalue to be minus 5. Other eigenvalues you can get from here, because this is like a 2 cross 2 matrix. Understandable? So what I will be getting here is that lambda square minus the trace, which is 5 lambda, plus 3 into 2, 6 minus 1, that is 5. Okay, so then lambda is minus b plus minus under root b square minus 4ac upon 2a. Okay, so these are the values of lambda. So what all are the absolute values? So absolute values will be here, magnitude of lambda 1 will be 5 plus magnitude of 5 plus under root 5 by 2. 5 plus under root 5 by 2. 5 plus under root 5 by 2. This will be a positive value, no? This will also be a positive value. So what you can do? 5 by 2 plus under root 5 by 2 plus 5 by 2 minus under root 5 by 2. We are just adding up these values. Just I need to take the magnitude. Here I took the magnitude. This as it is, this as it is, because they are the positive values only. So this is and this is getting cancelled out. Answer is 10. This is the correct answer. This is the correct answer. What they are talking about? They are talking about the absolute values. So what is the correct answer? 10. Understandable? How did we do it? We did it with a very easy calculation. The only thing we need to do is that B is a diagonal matrix. It will have the diagonal elements same as the eigenvalues of A. So we need to find out the eigenvalues of A. Someone was very smart. He thought that, sir, okay, this value I need to find out. That means I need to find out the summation of lambda 1 plus lambda 2 plus lambda 3. So that will be equivalent to trace of A. So I simply find out the trace of A. But they asked about that absolute value. Absolute means magnitude. That means now you need to find out the eigenvalues. So I found out the eigenvalues. The eigenvalues came out to be this. Then I took the magnitude. Answer came out to be 10. Understandable? Well and good. Let's go to the next question. So here concept of diagonalization has ended. Concept of diagonalization has ended. Okay. Next we are going to see about some special matrices, like real symmetric matrix is a special matrix, no? Real symmetric matrix. It is a special matrix. So their eigenvalues are always real. That we need to prove. For a real symmetric matrix, eigenvalues are always real. This is what we are proving. Sir, why the proof is important? It is a gate examination. It is a numerical examination. Proof is important. It is important. With time you will realize that it is important. Okay. So what is given? It is real symmetric matrix. Real symmetric matrix. So for real symmetric matrix, what is the meaning of symmetric matrix? Sir, A transpose should be equals to A. One more thing you will let me know, A conjugate will also be equals to A only, no? Why is that so? Because what is conjugate? Conjugate means transpose of A. Sorry, conjugate means first you take the conjugate, then you take the transpose. Now if it is real, if A is real, then there will not be any impact of conjugate, right? Because all the elements are real, no? So for a real element, what is the conjugate of 2? That will be 2 only. What is the conjugate of 3? That will be 3 only. What is the conjugate of -3? That will also be 3. So no impact. What does that mean? A conjugate is also coming out to be A. So if it is a real symmetric matrix, that means it will be Hermitian matrix as well. Real symmetric means it will be Hermitian as well. Is that clear to you? So we are going to use two kind of properties. Here we are having two properties. Both of these properties we are going to use. Why is that so? Because I need to prove something is real or imaginary. So let's check that out, how we will prove it. So what is given? Ax equals to lambda x. What I am assuming is that A is a matrix which is having lambda as eigenvalue and x is the eigenvector. So Ax equals to lambda x. On both of the side I am taking conjugate. On both of the side I am taking conjugate. Do you remember this property? Right? Now this is a scalar value. When it will come out, what will happen? Conjugate. I hope you remember. K theta was K conjugate A theta. Right? This property we are applying. So it will come out as conjugate x theta. Okay? Understandable? Now let's make this as equation 1, this as equation 2. Now from equation 1 what we can do? Now basically I cannot proceed further. I need something x theta, A theta, and yeah, one more thing. This A conjugate could be written as A only, no? A conjugate could be written as A only. Now I don't have anything called x conjugate multiply with A. I don't have anything. But I have equation A. I have equation 1, sorry, not A. I have equation 1. From equation 1 what I can do? I can do the pre-multiplication of x theta. What I am doing? Pre-multiplication of, I should not say x theta, it is just the language I am using. It is actually x conjugate. Pre-multiplication of x conjugate I am doing. If I do the pre-multiplication of x conjugate, what I will get? X conjugate Ax lambda x conjugate x. Understandable? Now from equation 2, can I put the value of x conjugate A? Yes. From equation 2, what I will do? X conjugate A is nothing but lambda conjugate x theta into x. Right? X conjugate A is nothing but lambda conjugate x theta into x. Basically this we are doing. This we are replacing. Lambda conjugate x theta, lambda conjugate x theta, and that is lambda conjugate x theta, that is equivalent to this one, which is lambda x conjugate x. From this expression what you can tell? That lambda conjugate is coming out to be lambda only. There you go. Basically what we have done, this was the expression that I got from in equation 1. I did the pre-multiplication of x conjugate. So x conjugate I did the pre-multiplication, x conjugate A x equals to lambda x conjugate x. So x conjugate into A could be replaced as lambda conjugate x conjugate, lambda conjugate x conjugate, and this remains as it is. This remains as it is. So these two guys remains as it is. This one remains as it is. And let's remove this one because you guys will be getting confused. So what I am doing is that I will put this value here, and I will say that this has been put here. So you will be able to remember that what we are doing. From equation 1 we are putting up this value and we are putting it here, and then this remains as it is. So lambda conjugate is coming out to be lambda. What does that mean? That means lambda is real. Lambda is real. So what you will remember? You will remember as a statement as well. For a real symmetric matrix and for a Hermitian matrix as well, the eigenvalues are always real. The eigenvalues are always real. Okay. Which of the following statements are true? In that kind of questions, these questions could be asked. For a real symmetric matrix, the eigenvalues are always real. Yes, it is true. Okay. Another statement. For a real symmetric matrix, eigenvectors corresponding to different eigenvalues are orthogonal to each other. Are they independent? Yes, it is pretty sure. For any kind of matrix, eigenvectors are always eigenvectors are always independent of each other. But if it is real symmetric matrix, then they will be orthogonal as well. We need to prove that. Understandable? So let's just say I am having, for matrix A, I am having two eigenvalues, lambda 1 and lambda 2, and their corresponding eigenvectors are v1 and v2. So what I can write down? A into v1 would be lambda 1 into v1, and A into v2 would be lambda 2 into v2. Understandable? If I need to prove the orthogonality, what I need to prove? If I need to prove the orthogonality, then v1 transpose into v2 and v2 transpose into v1 should be equals to 0. This is what I need to prove. I hope you remember the orthogonality rule, right? This is what I need to prove. That means I need somewhere v1 is this vector, no, and v1 transpose row multiply with column. Yes, it is fine. So v2 transpose, if I multiply, will I get anything? Pre-multiplication. Yes, I need to do the pre-multiplication. So let's pick up this equation. This is our equation 2. So in equation 1, what I'm doing? I'm doing the pre-multiplication of v2 transpose. V2 transpose. Why I'm doing so? Because what I will get? Here you will get v2 transpose A into v1, but lambda 1 v2 transpose into v1. Somehow I need to make this form, no? v2 transpose into v1. Somehow I need to make this form. So this form I have made, v2 transpose into v1. Understandable? So this is something that we have done. Next, is there anything we can use? What we can do here is that, yes, what you do here, you take the transpose on both of the side, taking transpose How I am thinking all these things? Because here I would need v2 transpose. From here I can get v2 transpose. How will I get? If I take the transpose on both of the side. So what I will get? v2 transpose into A transpose, that would be equals to lambda 2 into v2 transpose, right? Lambda 2 will simply come out v2 transpose. So what is A transpose? Since it is real symmetric matrix, so A transpose is nothing but A only. So v2 transpose into A equals to lambda into v2 transpose. Is that clear to you? What I have done here? Let's call this as equation 3. Now from equation 3, so v2 transpose into A is nothing but lambda into v2 transpose into v1. That would be equivalent to lambda into v2 transpose into v1. This proof is not very straightforward, but yeah, we need to keep on thinking that v1 into v2 transpose I would need. So here I did the pre-multiplication with v2 transpose so that I can get v2 transpose into v1. Then I thought that I cannot proceed further. I need something about v2 transpose. So here I tried creating v2 transpose. So this is what I was getting, v2 transpose into A. So v2 transpose into A was nothing but lambda 2 into v2 transpose. So from here what I am getting? This side comes here. So I can take v2 transpose into v1 as common. So what I will get? Lambda 2 minus lambda 1 v2 transpose into v1. I hope you are understanding what I have done. Minus lambda 1 v2 transpose into v1. So v2 transpose into v1 I have taken common. So inside lambda 2 minus lambda 1 will be left. Will be equals to 0. Now what is given? That lambda 1 and lambda 2 are different, corresponding to different eigenvalues. So lambda 1 is not equals to lambda 2. That means they cannot be 0. So who has to be 0? This guy has to be 0. What does that mean? From here, what I can prove is that v2 transpose into v1 would be equals to 0. There you go. What does that mean? v1 and v2 are orthogonal to each other. That's it. So for a real symmetric matrix, we have seen 2 points. What was the first point? For a real symmetric matrix, eigenvalues are real, and the eigenvectors corresponding to different eigenvalues are orthogonal to each other. I could have shown this example only and I could have very easily said whatever that I proved here. But we need to choose the tougher path, because these kind of questions are being asked nowadays. These kind of questions are being asked nowadays. They are asking these kind of questions where the proof is required. Otherwise, what I could have done? I would have simply taken a matrix A. Is it a matrix A? Is it a real symmetric matrix? Is it a real matrix? Yes, sir. Is it symmetric as well? Yes, sir. Real symmetric matrix. Can I find out its eigenvalue? Do it on your own and find out the eigenvalue. It is coming out to be 114. So with respect to lambda equals to 1, I find out the eigenvectors, which were v1 and v2. And with respect to lambda equals to 4, I find out the eigenvectors, which were v3. First thing, that eigenvalues are real. Eigenvalues are real. This is the first thing that I can prove. Eigenvalues are real. It is not a proof, no. It is not a proof, right? The proof is here. But here I can say that, yes, eigenvalues are real. What is the other thing I can say? Someone will say that, sir, v1 is perpendicular to v2. These are the eigenvalues corresponding to lambda equals to 1. v1 is perpendicular to v2? No. No. It is not necessary. Eigenvectors corresponding to different eigenvalues should be perpendicular. That means v1 should be perpendicular to v3. Yes. v2 should be perpendicular to v3. Yes. These are yes. Eigenvectors corresponding to different eigenvalues should be perpendicular. You can say 1 into 1, 1, minus 1 into 1, minus 1. 1 minus 1 will be 0. 1 into 1, 1. 0 into 1, 0. Minus 1 into 1, minus 1, 0. So v1 and v3 are perpendicular, v2 and v3 are perpendicular, but v1 and v2 need not to be perpendicular. Okay. Eigenvalues, what is written? Eigenvectors corresponding to different eigenvalues should be orthogonal to each other. So for a real symmetric matrix, there are two properties. Can you let me know those properties? Yes, sir. The properties are eigenvalues are real and eigenvectors corresponding to different eigenvalues are orthogonal to each other. That's it. Is that clear to you? Now something about skew symmetric matrix we will see, but before that, let's see something about orthogonality. So are they orthogonal to each other? How will you check? Sir, 1 multiply with minus 1. This I have already told in one of the basic videos. I have already told how to check the orthogonality. 1 multiply with minus 1, 2 multiply with 1 plus 1 multiply with minus 1. So what is the answer you are getting? 0. That means yes, orthogonal. They are orthogonal to each other for sure. Right? Is this real? Is this a real vector? Yes, sir. Is this a real vector? Yes, sir. So I will say they are orthogonal over real plane. Over real plane. Orthogonal over real plane. Now here I need to check the orthogonality. So someone will say that, sir, how will I check the orthogonality? Is it real? No. It is complex. This is a complex vector and this is also a complex vector. So how will one guy check the orthogonality? He will say, sir, I will multiply I with iota with minus 1, then I will multiply minus 2 with iota, then I will multiply minus iota with 1. So what is the answer I am getting, sir? Minus iota, minus 2 iota and minus iota. So sir, I am getting minus 4 iota. They are not orthogonal. But this method is wrong. Okay. So whenever you check the orthogonality over a complex plane, okay, orthogonality over a complex plane, because values are complex, right? Orthogonality over complex plane, if you check, then what you need to do is that you need to take the conjugate of one and second one as it is. What I mean to say is that I will take the conjugate of this vector. What is this vector? Iota. So what will be the conjugate of iota? Minus iota. Second one as it is. That means minus 1 as it is. Plus conjugate of minus 2. What that would be? Minus 2 only. Because what is the meaning of conjugate? Iota will be replaced with minus iota. Rest everything will be as it is. And second one as it is. Iota will remain as it is here. This will remain as it is. This will not change. Only conjugate of one vector only. This, what will happen to minus iota? Minus iota will become plus iota and this one will remain as it is. What is the summation we are getting? This is iota, this is minus 2 iota and this is iota. What is the answer we are getting? 0 only. Or what I could have done, let's keep this as it is, iota as it is, and conjugate of this one. What is the conjugate of minus 1? That will be minus 1 only. Plus minus 2 as it is. What is the conjugate of iota? That is minus iota. Plus minus iota as it is. What is the conjugate of 1? That is 1 only. So what you are getting? Minus iota plus 2 iota minus iota, that is also 0. That means yes, they are also orthogonal, but they are orthogonal over complex plane. There is very rare chance that this will be asked in the examination, but who knows, it can be asked. So when I say orthogonal over real plane, this is what I mean. Orthogonal over complex plane, this is what I mean. Understandable? And do you remember one more thing? Do you remember one more thing from basics? What is the meaning of a skew symmetric matrix having odd order? What will be its determinant? So that will be 0. And here it could be non-zero or 0 as well. I guess in basics when I was teaching this topic here, I said that it will be always non-zero, but it could be 0 as well. Okay. Do you remember skew symmetric matrix of odd order? Skew symmetric matrix of odd order will have 0 determinant, but a skew symmetric matrix of even order may have non-zero determinant. Do you remember this thing or not? And here we will prove it. We will prove it here. But do you remember this thing? The skew symmetric matrix of odd order will have 0 determinant, and skew symmetric matrix of even order will have non-zero determinant. What I mean to say is that, let's just say if this is the matrix, and I am saying that it is skew symmetric matrix, then its determinant will be 0. And if this is the matrix, then its determinant might be 0 or non-zero, 0 or non-zero, or 0 as well, whatever the possibility is there. But skew symmetric matrix of odd order will have 0 determinant. Okay. Prove that for a real skew symmetric matrix, eigenvalues are either purely imaginary or 0. Real skew symmetric matrix. Real skew symmetric matrix. So again it is real, that means A transpose would be equals to A. And what will be your A conjugate? That is given as, sir, A conjugate and then transpose. A conjugate is equals to minus A only. So sir, it could be written as minus A transpose, or it could be written as minus A. That means eventually you are getting A conjugate equals to minus A. So what this is known as? Hermitian. Sorry, skew Hermitian. Not Hermitian, skew Hermitian. This is known as skew Hermitian. And what this is known as? This is known as skew symmetric. So a real skew symmetric matrix will also be skew Hermitian matrix. Skew symmetric matrix. A real skew symmetric matrix will also be skew Hermitian matrix for sure. What we need to prove? It will be either purely imaginary or 0. So what we can say is that A is a matrix eigenvalue lambda eigenvector x. So Ax equals to lambda x. What you do? Take conjugate x theta A theta lambda conjugate x theta. X conjugate as it is. What this A conjugate is? This is minus A lambda conjugate x conjugate. Let's call this as equation 1 and this as equation 2. Right? Now what I will do? I will do that here in equation 1 pre-multiplication of x conjugate. So x conjugate Ax would be equals to lambda x conjugate x. Now what is this equivalent to? From here you can sense that x conjugate A is minus lambda conjugate x conjugate. So minus lambda conjugate x conjugate equals to x will be lambda x conjugate x. Simple thing, right? If you compare, lambda is coming out to be minus lambda conjugate is coming out to be lambda. That means lambda is coming out to be minus lambda conjugate. What does it show? That lambda has to be purely imaginary or 0. Do you know this thing? Let's just say if lambda is 2j, then what will be its lambda conjugate? That will be minus 2j. Can I write it down as minus lambda? Yes, sir. Lambda conjugate is coming out to be as minus lambda. So if lambda is 2j, then lambda conjugate will be minus 2j. Can I write it down as minus lambda? Yes, sir. Lambda conjugate is coming out to be as minus lambda. What does that mean? Lambda is purely imaginary. Or it could be 0 as well. How it could be 0? Lambda is 0. What is lambda conjugate? That is also 0. Can I write it down as minus 0? Yes. Can I write it down as minus lambda? Yes. So there are two options. eigenvalues could be either 0 or purely imaginary. Is that understandable to you or not? Either 0 or purely imaginary. This we have proven. Similarly, they will be orthogonal to each other as well, but they will be orthogonal over complex plane, because eigenvalue is imaginary, then eigenvector can also be imaginary. So if eigenvectors are imaginary, if these eigenvectors are imaginary, then they will be orthogonal over complex plane. So whatever the property was there in a real symmetric matrix, the same property is there in real skew symmetric matrix. So what does the property says? For real symmetric matrix, eigenvalues were real. For real skew symmetric matrix, eigenvalues are purely imaginary or 0. Purely imaginary or 0. And what about the eigenvectors? They will be orthogonal to each other as well. Now, can you think that why this statement is correct? Because let's just say A is my 3 cross 3 matrix, and it is real skew symmetric matrix. Okay, it is real skew symmetric matrix. So I will have 3 eigenvalues, lambda 1, lambda 2, and lambda 3. Okay. Let's just say one of the eigenvalue is 2j. I told you one thing. And what you can comment about lambda 1, lambda 2, lambda 3? That sir, they will be purely imaginary or 0. So is it purely imaginary? 2j? Yes. Can you comment on the second eigenvalue on your own? I told you if it is a real matrix, then eigenvalues will be always complex conjugate. So other eigenvalue will be nothing but minus 2j. Now can you comment about the third eigenvalue? What option you are having? Either it could be purely imaginary, or it could be 0. Can it be a purely imaginary value? If it is a purely imaginary value, let's just say 4j, then where is minus 4j? Sir, it cannot be possible. That means it cannot be purely imaginary value. That means the third eigenvalue has to be 0. So this will be the eigenvalue. For a 3 cross 3 skew symmetric matrix, I have given the eigenvalues 2j only. So with respect to 2j, you know that minus 2j will also come. Now the third eigenvalue you can comment on your own. Why you can comment? Because sir, I am having only two options, either purely imaginary or 0. Can it be purely imaginary? No. If it is purely imaginary, then its complex conjugate should also come. But complex conjugate is not even available. It will not come. So it has to be 0. And now if these are the eigenvalues, what will be their multiplication? Lambda 1, lambda 2, lambda 3. Their multiplication will be 0. And what does the multiplication of eigenvalue show? That shows the determinant. And determinant will come out to be 0. There you go. Okay. So this is how all the things are interrelated. Please don't think that sir, there is too much of information. We will write down all the conclusion. So if all the conclusion will be written at one place, then it will not feel like too much of information. Okay. So don't worry about sir, how we will remember all these things. Only thing you need to remember, symmetric matrix eigenvalues will be real. Real symmetric matrix eigenvalue will be real. Eigenvectors corresponding to different eigenvalues will be orthogonal to each other. Then skew symmetric matrix. Skew symmetric matrix eigenvalues will be purely imaginary or 0. And eigenvectors corresponding to different eigenvalues will be orthogonal to each other. Example. What kind of matrix it is? A transpose equals to minus A. Right? So it is a skew symmetric matrix. And is it a real matrix? Absolutely. So real skew symmetric matrix. What all are the eigenvalues you are getting? Either purely imaginary or 0. What are the eigenvectors? This is the eigenvector, this is the eigenvector, and this is the eigenvector. They will be called different eigenvalues. Okay. Don't say that sir, under root 5j and under root minus 5j both are same. No, they are different. They are different. They are different. They are different. So you will see that what you will see, V1 is perpendicular to V2 is perpendicular to V3. Okay, they will be perpendicular to each other. Here also same scenario, that V1 will be perpendicular to V2. They are the different eigenvalues. Two different eigenvalues I am getting, purely imaginary. Okay, and again it is also a real skew symmetric matrix. So with respect to example, if you want to remember, you can remember with respect to example, but proof are also important. At least do the proof at least once in your rough notebook. Okay, at least once. This proof you do, this proof also you do. This is very important actually. This is the most important one. This property is the most important one. 99% chances are there that proper question would come from here only. Okay, and this is also important. Understandable? So with respect to example we have seen. So whatever that we have studied, do you remember the brothers? I told you that a symmetric matrix is the brother of a Hermitian matrix, right? They are the brothers. And skew symmetric is the brother of a skew Hermitian. Do you remember this friendship, skew Hermitian? Here what was the property? A transpose equals to A. Here what is the property? A conjugate equals to A. Here what is the property? A transpose equals to minus A. Here what is the property? A conjugate equals to minus A. Do you remember this friendship? Yes sir, we remember. Right? So whatever the property that was there in symmetric matrix, the same property Hermitian will follow. Whatever the property that are there in skew symmetric, the same property skew Hermitian will follow. What is the property? This is your skew Hermitian matrix? Absolutely. H conjugate is giving you H only. What do you mean by conjugate, sir? Conjugate means first you take the conjugate and then you take the transpose. So this minus I comes here, this goes here. So conjugate and transpose is coming out to be matrix H only. Okay. So what are the eigenvalues you are getting? Real eigenvalues you are getting. Real eigenvalues. Right? Real eigenvalues you are getting. What about the eigenvectors? Are they orthogonal to each other? How will you check the orthogonality? They are orthogonal over complex plane. Orthogonal over complex plane. Here also they are orthogonal over complex plane. Minus I, minus iota, minus iota. Here also minus, minus iota. They are orthogonal over complex plane. So they will also be orthogonal. How will you check? One as it is, other one conjugated. Then iota as it is, other one conjugated. Minus iota conjugate will be iota only. So iota square is minus 1 only. So this is the answer you are getting. Here also, here they are luckily orthogonal over real plane, but they will be orthogonal over complex plane as well. Understandable? So here what eigenvalues you are getting? You are getting imaginary eigenvalues. Imaginary eigenvalues, or eigenvalues could be 0 as well. Imaginary eigenvalues or 0. 0 also you can get, but it is a 2 cross 2 matrix, that's why you are not getting it. And what kind of matrix it is? This was your Hermitian, right? And what this is, you can simply see that H conjugate is coming out to be minus H. So it is skew Hermitian matrix. It is skew Hermitian. You can calculate H conjugate. S conjugate you can calculate. What will be S conjugate? Take the conjugate and then transpose. So 0, 0, and this is which is coming out to be minus S only. So yeah, this is the condition we are getting. S conjugate is coming out to be minus S. So it is skew Hermitian and they are also orthogonal. So we will write down all the conclusion, don't worry. They are orthogonal to each other. Understandable? So let's see the conclusion. First, let's talk about the eigenvalues. So for real case, for a real symmetric matrix and for a Hermitian matrix, eigenvalues are real. For skew symmetric matrix and skew Hermitian matrix, eigenvalues are either purely imaginary or 0. Will you be able to remember it? Absolutely clear, sir. What about orthogonality? So eigenvectors corresponding to different eigenvalues are always orthogonal to each other for all the cases. For real symmetric as well, for Hermitian as well, for skew symmetric as well, for skew Hermitian as well. For all the cases, eigenvectors will be orthogonal to each other, but in case of real symmetric matrix, they will be orthogonal in real space, and in case of others, they will be orthogonal in complex plane. You can see that here vector came out to be complex, here vector came out to be complex, here vector came out to be complex. Here luckily they came out to be real, but they could be complex as well. So it will be orthogonal over complex plane. And why they will come out to be complex? Look, this is the case of skew symmetric matrix, right? You know that eigenvalues are imaginary. Eigenvalues are imaginary, so their eigenvector would be complex. Here also you know that eigenvalues are imaginary, so their eigenvector may be complex. Here eigenvalues are real, but the matrix is imaginary, no? Eigenvalues are real, but the matrix is imaginary. That means eigenvectors could be imaginary, right? But what about the real symmetric matrix? Real symmetric matrix. Real symmetric matrix. So here matrix is also real, and eigenvalues are also real. So eigenvector will also be real. Real, 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 real. In rest of the cases, there could be complex values, but in case of real symmetric matrix, they will be always real. So very simple properties are there. We will be able to remember that for a real symmetric matrix and Hermitian matrix, eigenvalues will be always real. For a skew symmetric matrix and skew Hermitian matrix, eigenvalues will be either purely imaginary or 0. What about orthogonality? All the eigenvectors corresponding to different eigenvalues will always be orthogonal to each other in all kind of cases. There is something about diagonalization as well, that it will be always diagonalizable over real plane and over complex plane. What do you mean by diagonalizable? That means it will give you 3 linearly independent eigenvectors. If it is a 3 cross 3 matrix, if it is a n cross n matrix, it will give you n linearly independent eigenvectors. and linearly independent eigenvectors. Okay, and if the eigenvectors are real, if these eigenvectors are real, or if the eigenvectors are complex. So if eigenvectors are real, then it is known to be diagonalizable over real plane, otherwise it is known to be diagonalizable over complex plane. Okay, so what do you know about real symmetric matrix, real skew symmetric matrix, Hermitian matrix and skew Hermitian matrix? What do you know about them? Sir, for the eigenvalues, eigenvalue of a real symmetric matrix and Hermitian matrix will be real, and what about the eigenvalues of a skew symmetric matrix and skew Hermitian matrix? They will be, sir, either purely imaginary or zero. What about orthogonality? Orthogonality, eigenvectors corresponding to different eigenvalues will be orthogonal to each other. What about diagonalization? All of them will be diagonalizable. That's it. This is the conclusion you need to remember about these four matrices. What four matrices we are talking about? Symmetric, skew symmetric, Hermitian, skew Hermitian. There were one more friend of them. Do you remember that friend? Orthogonal matrix. Do you remember orthogonal matrix? Orthogonal matrix. The eigenvalues of orthogonal matrix lie on the unity circle, i.e. magnitude of all the possible eigenvalues is 1. So this also we need to see. Do you remember orthogonal matrix? What do you mean by orthogonal matrix? Let A be a orthogonal matrix. So what does that mean? A into A transpose would be equals to I. Right? So we need to find out the eigenvalue of A into A transpose. Or we need to comment something that that magnitude of all of them will be equals to 1. So how we will do it? Let me take a break and then I will come back. You try doing it on your own. What do you know? Ax equals to lambda x, you know. Only one thing you know, Ax equals to lambda x. We need to prove, what we need to prove? That if this is having an eigenvalue of lambda and eigenvector of x, then magnitude of lambda is 1. This is what we need to prove. Okay, so try doing it on your own. I will take a break and then I will come back. Yeah, so did you try this question? Matrix A is having eigenvalue of lambda and eigenvector of x. So what I am thinking is that I will put Ax equals to lambda x, right? Now what we are talking about? We are talking about the magnitude, no? Magnitude of all possible eigenvalues. So we are talking about the magnitude. So let's take the magnitude on both of the side. This is also a vector. This is also a vector. So let's take the magnitude on both of the side. Ax is a vector only, no? Let's just say Ax is some n cross n. So what will be x? X will be n cross 1. So what will be the equivalent? Equivalent will come out to be n cross 1 only. So it is a vector. It is also a vector. X is also a vector. So they are the vector only, right? So let's take magnitude on both of the side. Understandable? Let's try solving this one now. What this would represent? What this would represent? So this would simply represent, can I write it down in this manner? Is that correct? Magnitude of x square was x transpose into x. So here it should be square. Can I write it down in this manner? Absolutely, sir. So can I write down x transpose into A transpose? If I open it up, what I will get? X transpose into A transpose. Multiply with A, multiply with x. A transpose into A, what that is? A transpose into A. That is equals to I only, because it is a orthogonal matrix. So that is equals to I. So what you are getting? X transpose into x, what that is equivalent to? Magnitude of x whole square. So magnitude of Ax whole square is coming out to be magnitude of x whole square, or what you can say, it is coming out to be nothing but magnitude of x only. So magnitude of Ax is coming out to be magnitude of x for orthogonal matrix. So for orthogonal matrix, this is equivalent to x only. Let's just say there was a vector x, a I cap plus b j cap plus c k cap, and I multiply this vector x with the lambda. So lambda could be any value, no? It could be real value as well, it could be imaginary value as well, right? So lambda a I cap plus lambda b j cap plus lambda c k cap, right? And lambda I am taking common. So if I take the magnitude, what will be the magnitude here? Under root a square plus b square plus c square. Here also if I take the magnitude, so when I am taking the magnitude here, I need to take mod of lambda, no? Let's just say lambda is some negative value minus 2x. And here I am saying that magnitude of x is 5. So what will be the magnitude of minus 2x? That will be 10 only, not minus 10. So you need to take the magnitude, no? Magnitude. So if I am saying that magnitude of, what will be the magnitude of lambda x? What will be the magnitude of lambda x? So that will be equivalent to magnitude of lambda multiply with magnitude of x. Do you understand this point or not? Is that clear to you? Magnitude of lambda x would be equivalent to magnitude of lambda multiply with magnitude of x, and that is coming out to be equivalent to magnitude of x only. So from here magnitude of x and magnitude of x is getting cancelled out, and what you are getting, magnitude of lambda equals to 1. There you go. This is the answer. Okay, what does that mean? The eigenvalues of an orthogonal matrix lie on unity circle. This is the equation of a unity circle. You will understand. Okay, when we study calculus, you will understand this is the equation of unity circle, or you can say that the magnitude of eigenvalue, the magnitude of all possible eigenvalues will be 1 for an orthogonal matrix. Understandable? Now someone would say that, sir, why you did all those things? What you could have done is that, let's apply Cayley-Hamilton theorem. So what will be the eigenvalue of A? That will be lambda. What will be the eigenvalue of A transpose? That will also be lambda, sir. That is equals to, and what will be the eigenvalue of I? That will be equals to 1. So lambda square equals to 1. So here your answer is coming lambda square equals to 1. And here I am saying that magnitude of lambda should be equals to 1. Are both of them same? No, this is different. So that means there is something wrong here. What is wrong? This is wrong. This particular calculation is wrong. Why it is wrong? Are both of them having same eigenvector? If they were having same eigenvector, no, then you can apply this Cayley-Hamilton theorem. Like basically a cube plus a square minus 2a plus I. What will be the eigenvalue you used to write down? Lambda cube plus lambda square minus 2 lambda plus 1. All of them are having the same eigenvector. If all of them are having the same eigenvector, then you can apply the Cayley-Hamilton theorem, and not here, because A transpose is having a different eigenvector than A. So you cannot apply that Cayley-Hamilton theorem here. CS theorem you cannot apply here. So what is the most important point here? Why it is wrong? Because A and A transpose have different eigenvector. Right? So why this is wrong? That we have understood. Here lambda square equals to 1 is the answer we are getting. No, someone would say that, okay, the square of eigenvalue should be equals to 1. No, the magnitude of eigenvalue should be equals to 1. For an orthogonal matrix, the square of eigenvalue should be equals to 1. Is that a correct statement? No. The magnitude of eigenvalue should be equals to 1. How did we get it? How did we understood? Sir, Ax equals to lambda x. We talk about the magnitude, so took the magnitude. I want to understand what this is representing. So magnitude of Ax square will represent Ax transpose into Ax. Although this particular thing we have already done in one of the video. In one of the question I asked you, in basics I asked you that if A is your orthogonal matrix, then what is the relation between magnitude of Ax and the magnitude of x? Do you remember that question? The answer came out to be this one. This was the answer. Do you remember that question? Okay. So this is the answer we are getting, and from here, if we are taking out lambda, it will come out as the magnitude of lambda. So magnitude of lambda should be equals to 1. So for an orthogonal matrix, the magnitude of eigenvalue is 1. Another property. And rest all properties are same as previously. Basically, and do you remember the brother of orthogonal matrix? Do you remember the brother? The brother was unitary matrix, right? The brother was unitary matrix. What was the property of unitary matrix? Here A into A transpose equals to I. It was A into A conjugate equals to I, or you can say A conjugate into A. So brother of orthogonal matrix was unitary matrix. So these are the properties. For an orthogonal matrix and unitary matrix, magnitude of all the eigenvalues is 1. Orthogonality, they will be orthogonal. Eigenvectors corresponding to distinct eigenvalue will be orthogonal. And what about diagonalization? They are diagonalizable as well. So properties are same, only the eigenvalues properties are different. So if we conclude, what we can conclude? For real symmetric matrix and Hermitian matrix. For real symmetric matrix and Hermitian matrix, eigenvalues will be real. For skew symmetric matrix and skew Hermitian matrix, eigenvalues will be either purely imaginary or 0. For orthogonal and unitary matrix, eigenvalue will have unity circle, or you can say eigenvalue will be having a magnitude of 1. These three conclusions we can talk about eigenvalues. For orthogonality, all of them will be orthogonal to eigenvectors corresponding to different eigenvalues will be orthogonal to each other. What about diagonalization? All of them will be diagonalizable. So this orthogonality and diagonalization is not a matter of concern. Only eigenvalue is a matter of concern. For orthogonality, we just need to remember that eigenvectors corresponding to different eigenvalues are orthogonal to each other. So this is the conclusion of everything, but these proofs were also very important. These proofs are also important. I would have taken simply the examples like this, and then I would have said that these are the properties, but it will not make a good understanding. Okay, and why sir good understanding is necessary? We will solve one of the gate PYQ. There you will see that yes sir, good understanding was actually necessary. Okay, so that good understanding is actually necessary. Why it is necessary? Because gate is asking good question in these kind of topics. Okay, so they are asking good questions. That's why the understanding is necessary. So understanding is also we are having, and along with that, properties are also we are having. And in the end, we will write down all the properties together as well. So don't worry. One complete slide is there. Understandable? So one complete slide is also available. So don't worry that sir where we will write down the conclusion and everything. Everything I have thought of it. Okay. Let's see three more type of matrices. Three more type of matrices are there. First one is involutory, then idempotent, and then nilpotent. What is the meaning of involutory? Involutory means A square equals to I. And what is the meaning of idempotent? A square equals to A. And what is the meaning of nilpotent? A to the power k should be equals to 0. This is the meaning of nilpotent. Let's see example by example. Involutory. How will you remember? Involutory. In. So involutory A square equals to I. ID. Idempotent. ID means identical. So A square equals to A. And what is the meaning of nilpotent? A to the power k equals to 0. Will you be able to remember? Yes sir. Let's see the example of involutory. This was your matrix A. Okay. You do the A square. What you will get? This is identity matrix. No? Do the A square. You will get A only. This is your matrix A. Do the A square. What you will get? You will get A only. This is your matrix A. Do the A square. What will be A square? Sir, it will be 0, 1, 1, 0. Do the multiplication. 0, 1, 1, 0. So what you are getting? 0 multiply with 0. 1 multiply with 1. Wait a second. 0, 1, 0, 1, 1, 0, 1, 0. So this is not involutory. 0, 1, 1, 0. This is not involutory. Right? Here we are getting 1 only. Here we are getting 0. Here we are getting 0. And oh sorry, it is involutory. Sorry guys. A square equals to I. Sorry guys, A square equals to I. Involutory means A square equals to I. Sorry guys, blunder from my end. Okay, involutory means A square equals to I. A square equals to I. So A square equals to I, or here also I am getting A square equals to I only. Okay, so what we are getting here? A square equals to I. So in all the cases we are getting A square equals to I. What all are the eigenvalues here? What all are the eigenvalues? Eigenvalues are 1, 1 in this case. And here what all are the eigenvalues? Here eigenvalues are minus 1, 1. And here what all are the eigenvalues? In this case, eigenvalues you can find that is 1 and minus 1. Okay, these are the eigenvalues you can find on your own. It will come out to be 1 and minus 1. Here the eigenvalue is minus 1, minus 1. Here the eigenvalue is 1, 1. Okay, so they are the involutory matrix. These are the eigenvalues. Now, A square equals to I. Can I apply Cayley-Hamilton theorem? Yes, sir. Because A square and A both will have the same eigenvector. So can I put this as lambda square equals to 1? From here what you are getting? Lambda equals to plus minus 1. That means the eigenvalue for involutory matrix will be either plus 1 or minus 1. So here you are getting 1, 1, here you are getting minus 1, minus 1, here you are getting 1, minus 1. So either it will be plus 1 or it will be minus 1. So for involutory matrix, the eigenvalue will be either plus 1 or minus 1. What about idempotent matrix? What would be the eigenvalues for idempotent matrix? Sir, A square equals to A. That means I can apply Cayley-Hamilton theorem. Lambda square equals to lambda. What solution you will get? Lambda square equals to lambda. I can solve in this manner. Lambda square minus lambda equals to 0. Lambda I take common. Lambda minus 1. Lambda I take common. Lambda minus 1 equals to 0. So from here you are getting lambda equals to 0 and 1. Lambda equals to 0 and 1. Is that clear to you? For idempotent matrix, either the eigenvalue will be 0 or it will be 1, or both of them are also possible. Let's see the example. Idempotent matrix. What will be A square here? A square will be equals to A only. You can do it. What will be the eigenvalues? Eigenvalues will be 0, 0 because it is a null matrix. Here, if you do the A square, what you will get? If you do the square of it, you will get I only. That means A square equals to A. What all are the eigenvalues? That are 1, 1. Here eigenvalues is 0, 0. Here eigenvalue is 1, 1. And let's take this example. Let's do the A square. What you will get? 0, 0, 0, 1. Do the square of it. 0, 0, 0, 1. What we are getting? 0, 0, 0, then 0 and 1. So what you are getting? A square equals to A. And if you check the eigenvalues, what will be the eigenvalues? Eigenvalue will come out to be 0 and 1 only. So eigenvalues are 0 and 1. Right? So eigenvalues will be either 0 or 1. Either 1 or minus 1. Okay? So here 0, 0 is also possible, 1, 1 is also possible, 0, 1 is also possible. Understandable? So you apply the Cayley-Mendel theorem and this is what you are getting. What about nilpotent matrix a to the power k equals to 1? So if I do a to the power 2 and I am getting 0, what does that mean? It is known to be A is a nilpotent matrix. A is a nilpotent matrix of index 2. Okay, if I get a to the power 3 equals to 0, so it is known to be A is a nilpotent matrix of index 3. And if I do a to the power k equals to 0, what does that mean? A is a nilpotent matrix of index k. Okay, understandable? All good. So let's see the example. This is your matrix A. If I do A square, what I am getting? 0. So A square equals to 0 I am getting. What does that mean? A is a nilpotent matrix of index 2. Here I did B. B square was not equals to 0, but B cube is coming out to be 0. What does that mean? B is a nilpotent matrix of index 3. Okay, this is the meaning. What about the eigenvalues? Eigenvalue will always be 0, no? Lambda to the power k you take. Lambda to the power k equals to 0. That means lambda has to be 0 only. So for nilpotent matrix, eigenvalues will surely be 0. Is that understandable to you? Okay. So this is the meaning. Let's solve this question. Use your brain and get the correct answer. Okay. Which of the following statements are true? First one. For an involutory matrix, lambda equals to 1 will surely be one of the eigenvalue. What you will think, sir? Involutory. Okay. Involutory matrix means, sir, A square equals to I. Right, sir? So lambda square equals to 1. So lambda would be either plus 1 or minus 1. What they are saying, lambda equals to 1 will surely be one of the eigenvalue. Sir, lambda equals to 1 will be the eigenvalue, but this statement is wrong. What they are saying, lambda equals to 1 is surely one of the eigenvalue. It might happen, no, that both of the eigenvalues are minus 1 only. Is it an involutory matrix? Yes, sir, it is an involutory matrix. What is the eigenvalue? Minus 1 only. Is one of the eigenvalue is 1? No, one of the eigenvalue is not 1. Both of the eigenvalues are minus 1. Both of the eigenvalues are minus 1. Are you able to understand this point? So lambda equals to plus minus 1 you are getting. What does that mean? Either the eigenvalue will be 1 or it will be minus 1, or both of the eigenvalues are also possible. Either 1 or minus 1 or both of the eigenvalues are also possible. You see here, either 1 or minus 1 or 1 minus 1, both are possible. That means first statement is wrong. For an involutory matrix, lambda equals to minus 1 will also be a surely eigenvalue? No. For idempotent, lambda equals to 0 will surely be the eigenvalue? No. What is the meaning of idempotent? Sir, you will think, okay, idempotent means A square equals to A. That means, sir, lambda square equals to lambda. So from here, sir, lambda equals to 0 and 1, two possible condition we are getting. Does that mean that 0 will surely be one of the eigenvalue? No. 0 could be one of the eigenvalue. 1 could be one of the eigenvalue. But surely will one of the eigenvalue? No. Surely one of the eigenvalue? No. For nilpotent matrix, eigenvalues will be 0 only. Nilpotent. What is the meaning of nilpotent, sir? Nilpotent means, sir, a to the power k equals to 0. That means lambda to the power k equals to 0. So yes, lambda equals to 0 will surely be one of the eigenvalue. All the eigenvalues will be always 0. Here all the eigenvalues will always be 0. So did you understand this point? That's why I took this example. 1 1 minus 1 minus 1 1 minus 1. Here 0 0 1 1 0 1. Understandable? That's why these examples were taken. Now for nilpotent matrix are always non-invertible. 101% we are sure. Because if all the eigenvalues are 0, what does that mean? That means the determinant will simply be multiplication of all the eigenvalues. 0 multiplied with 0 multiplied with 0 will always give you 0. So yes, this is also correct. An involutory matrix is always invertible. Is that correct? Involutory matrix is always invertible. What will be the determinant? What will be the determinant? Determinant will be multiplication of eigenvalues. Eigenvalue could be either 1 or minus 1. What does that mean? Determinant could be either plus 1 or minus 1? Say yes or no. Determinant can never be 0, no? Why is that so? Because 0 is not the one of the possible eigenvalues. Only two eigenvalues are possible, either 1 or minus 1. Let's just say if eigenvalues are 1 and 1 only. So what will be the determinant? 1. If eigenvalues are minus 1 and minus 1 only, what will be the determinant? Minus 1. If eigenvalue is 1, if eigenvalues are minus 1 and minus 1 only, then determinant will be 1. And if eigenvalues are 1 and minus 1, then determinant will be minus 1. So either the determinant will be 1 or minus 1. So it will be surely invertible. Involutory matrix is surely invertible. Here you see the example. What is the determinant here? What is the determinant? So determinant is 1 here. What is the determinant here? Here also determinant is 1. And what is the determinant here? Sir, here the determinant is minus 1. So 1 or minus 1, only two are possible. Understandable? An idempotent matrix is may or may not be invertible. A idempotent matrix may or may not be invertible. Yes, it is true. Why is that so? Because eigenvalues are 0 or 1 possible. If one of the eigenvalue is, if all the eigenvalues are 1, then what will be the determinant? 1. If all the eigenvalues are, if one of the eigenvalues is 0, then what will be the determinant? 0. So here both of them are possible. Okay, you can see the example idempotent. Here what is the determinant here? Here determinant is 0, sir. Here what is the determinant? Here determinant is 1. And here what is the determinant? Here determinant is 0. So determinant would be either 0 or 1. Why is it so? Because of the eigenvalues. Eigenvalues will be either 0 0 or 0 or 1 1 1 or 0 1. So if 1 1 1 are the eigenvalues, then the determinant may be 1. And if determinant is 1, then it is invertible. Otherwise it is not invertible. So this is also true. If A plus B are involutory, then if A and B are involutory, then A plus B is also involutory. Yes, let's check that out. If A is involutory, what is given? A is involutory and B is also involutory. What we are checking? We are checking option I. Then we need to comment on A plus B. A plus B we need to comment on. So what do? We take the square of A plus B. So A square plus B square plus AB plus BA. This is the square. I told you A square plus B square plus 2AB. No, AB plus BA. That is the square. And if it is involutory, if A plus B is involutory, then A plus B whole square should be equals to I, right? If A is involutory, then A square equals to I. So if A plus B is involutory, then A plus B whole square should be equals to I. So this should be equals to I. So A square plus B square plus AB plus BA. But it is not necessary, no? What is the meaning of involutory? What they are saying, if A and B are involutory, then A plus B is also involutory. It is not necessary. Why is that so? Because I would be equals to, what is the value of A square? A square is given as I. What is the value of B square? B square is also given I. AB plus BA. Now from here what you can conclude? That AB plus BA plus I equals to 0. So A plus B will be involutory if and only if AB plus BA plus I equals to 0. If A and B are involutory, then A plus B is also involutory. That is wrong. But if A plus B, if AB plus BA plus I equals to 0, then A plus B will be involutory. Say yes or no. Is that clear to you? Given that, here also given that A and B are involutory. This condition should be given, no? Given that A and B are involutory. So scenario is that A and B are given involutory. A and B are given involutory. That means A square equals to I, B square equals to I. Now you need to comment on A plus B. So you did the square. These kind of questions we have seen in basics. In the similar manner we are solving. You did the square. Then what you are getting? AB plus BA plus I. I have assumed that A plus B is involutory. Then what is the condition I am getting? That this condition I am getting. So if this condition is satisfied, then it will be involutory. Otherwise it will not be involutory. Understandable? For a nilpotent matrix, nullity is always greater than or equals to 1. Yes, for sure. Why is that so? Because determinant is 0. For nilpotent, determinant is always 0. That's why it will be greater than or equals to 1. For involutory matrix, nullity is always 0. Involutory, determinant will always be non-zero. That means yes, nullity is always 0. What does that mean? Option L. Option L. Involutory. Involutory means determinant of A can never be 0. What does that mean? Determinant of A can never be 0. What does that mean? That means 0 can never be an eigenvalue. 0 can never be an eigenvalue. Because if 0 is an eigenvalue, then determinant would be 0. Now what they are saying, for a involutory matrix, nullity is always 0. Yes. What is the meaning of nullity of A? Nullity of A is geometric multiplicity of lambda equals to 0. Now what is arithmetic multiplicity of lambda equals to 0 for this case? That is 0, because no eigenvalue could be 0. That means geometric multiplicity of lambda equals to 0 should also be 0. What does that mean? That means nullity of A has to be equals to 0 only. There you go. Understandable, no? Because if nullity is greater than 1 or equals to 1, if nullity is there, that means determinant would be 0 only. If this is non-zero, then from here only you can comment that nullity is equals to 0 only. From here only I can comment that if determinant is non-zero, then nullity has to be 0. Because if nullity is non-zero, what does that mean? It is not a full rank matrix. If it is not a full rank matrix, then determinant would be 0. But determinant is non-zero, that means it is not a full rank matrix. That means if determinant is non-zero, that means it is a full rank matrix. And if it is a full rank matrix, that means nullity is 0. So statement L is also true. For idempotent matrix, nullity is always greater than 0. Is that true? No. Because for idempotent matrix, it is possible to have a non-zero determinant. And if determinant is non-zero, then what will happen? Nullity will be 0. So this statement is wrong. For idempotent matrix, it is possible to have a non-zero determinant. If a determinant is non-zero, that means there is no zero eigenvalue. If there is no zero eigenvalue, that means nullity of A would be equals to 0 only. So this statement is wrong. For an idempotent matrix, the nullity can be any value from 0 to n. Yes. It could be 0 as well, it could be 1 as well, it could be 2 as well, it could be 3 as well, it could be n as well. So yes, for idempotent matrix, the nullity could be anything. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 till n. Understandable? So these statements are absolutely understandable to you. Nothing you need to mug up. If you only remember this particular thing, then you will be able to write down every single answer. Okay. So here is the conclusion of everything that we have studied. What we studied first? Symmetric matrix A equals to A transpose. Eigenvalues are real, orthogonal in real space, always diagonalizable. A equals to A conjugate. Real eigenvalues will be there for Hermitian orthogonal. What about skew symmetric matrix? This is the condition. Purely imaginary or real, orthogonal, diagonalizable. Skew Hermitian, purely imaginary, orthogonal, diagonalizable. Okay, purely imaginary or 0. For this was for skew Hermitian. What about orthogonal? Orthogonal means the magnitude will be 1. Magnitude will be 1. Same goes for unitary as well. They are orthogonal in complex space. They are always diagonalizable as well. Okay, they will be orthogonal in complex space. What will be orthogonal? Eigenvectors will be orthogonal. Orthogonality of eigenvectors with respect to different eigenvalues. So they will be orthogonal. Now what about involutory? So orthogonality is not guaranteed. They are not guaranteed. Okay, we cannot comment about orthogonality. Can we comment about the eigenvalues? Yes, eigenvalues we can comment. Understandable? Diagonalizable? Yes, it is always diagonalizable. It is always diagonalizable, and it will never be diagonalizable, except if it is a null matrix. If it is a null matrix means, what is the meaning of null matrix? Null matrix means all are 0. All are 0 means eigenvalues are 0. And eigenvalues are 0, what does that mean? All are having the nullity of A. Here, what will be the nullity of A? Nullity of A will be n. What does that mean? Geometric multiplicity of lambda equals to 0 will also be equals to n. That means yes, it is all diagonalizable. And what will be the diagonal matrix of it? That will be the same matrix. Because what you will find out? P inverse AP. P will also be 0, 0, 0. P inverse will be 0, 0, 0. Everything is 0, 0, 0. That means there is no concept of diagonalization here. So forget about it. So all 0 matrix, there is no concept of diagonalization. Forget about it. It is not diagonalizable. Nilpotent matrix is not diagonalizable. Rest all are diagonalizable. Rest all are diagonalizable. Only nilpotent is not diagonalizable. And what about orthogonality? So for the first 6 cases we can comment on orthogonality, then we cannot comment anything. And what about the eigenvalues? That you have understood in a good manner. Understandable? All good? All fine? Let's see the questions related to this table. First one. This is a good question. Try it on your own. This is one question, then 2, 3 and 4. 4 questions you need to do. I will take a break and then I will come back. Okay, I need to drink some water. Roughly around 4 questions you will be able to solve in 30 minutes. Okay, so I will take a break and then I will come back. Try doing it on your own. Understandable? Okay. Yeah, so did you try this question? So first of all, what I would see, it is a real symmetric matrix. Real symmetric matrix is there and eigenvectors are also mentioned. So what do I know? For a real symmetric matrix, eigenvectors are orthogonal to each other corresponding to different eigenvalues. Corresponding to different eigenvalues, all the eigenvectors will be orthogonal to each other. Now, how do I know that these eigenvectors are corresponding to different eigenvalues? Are they corresponding to different eigenvalues? I don't know that. Then I went to this eigenvalues. I got to know that there is one eigenvalue 0, there is another eigenvalue 2, and there is another eigenvalue alpha. I don't know the value of alpha. But also it is given that algebraic multiplicity of lambda equals to 0 is 0. What does that mean? That means 0 is repeated only once. What does that mean? Alpha cannot be 0. Alpha cannot be 0 for sure. This is for sure that alpha cannot be 0. Why is that so? Because 0 is repeated only once. It will come only one time. Alpha could be 2. Alpha could be anything else as well. That I don't know. Now, how do I find out the value of alpha? Then what I thought, if it is a real symmetric matrix, then eigenvectors will be orthogonal. Corresponding to different eigenvalues. Right? But here what do I see? That if I do dot product of vector v and w, what I am getting? Minus 1 multiply with 1 plus 2 multiply with 1, 0 multiply with 1. What I am getting? 1 only. What do you get? That is 1. What does that mean? That means u and w are not orthogonal to each other. They are not orthogonal to each other. What does that mean? They are corresponding to the same eigenvalue. No, both will have the same eigenvalue, because if they were having the different eigenvalue, then they would be orthogonal to each other. If they are not orthogonal to each other, that means they will have the same eigenvalue. That means this particular matrix will have two eigenvalues same, and what that value has to be? Alpha cannot be 0, so alpha has to be equals to 2. Did you understand this point or not? So here we are having the eigenvalues 0, 2 and 2. Why the alpha value is 2? Did you understand this point or not? We got to know one thing, that v and w are not orthogonal to each other. But for a real symmetric matrix, eigenvectors corresponding to different eigenvalues are orthogonal to each other. But if they are not orthogonal, that means the eigenvalue has to be same. So eigenvalue either could be 2 or it could be 0. But it cannot be 0. Why is that so? Because it is written that algebraic multiplicity is 1 only. Algebraic multiplicity of eigenvalue lambda equals to 0 is 1 only. What does that mean? That means it is coming only once. Algebraic multiplicity is 1. That means it is coming only once. That means alpha has to be 2. So alpha value is 2. Next I need to find out the value of beta and gamma. So what I can say, that this eigenvector is corresponding to lambda equals to 0. This eigenvector is corresponding to lambda equals to 2. And this eigenvector is corresponding to lambda equals to 2. Now I know that u will be perpendicular to v. So what you will get if u is perpendicular to v? So 4 into minus 1 plus 2 into beta plus gamma into 0. That will be equals to 0. From here the value of beta is coming out to be minus 2. Right? Value of beta is coming out to be 2. Okay? And u is perpendicular to w as well. So from there what you will get? 4 into 1 plus beta into 1 plus gamma into 1, that would be equals to 0. So gamma will come out to be minus 6, because beta is 2. So 4 plus 2 6, gamma is coming out to be minus 6. So these are the values of alpha plus beta minus gamma. So what is the answer? Alpha plus beta minus gamma is coming out to be 10. Okay, that's the answer. So it was a very good thoughtful question. Here anyone would have said that, sir, they are perpendicular, so they would have found out the value of gamma and beta, but they would think what will be the value of alpha. So for thinking that, we got to know that w and v are not orthogonal to each other. So there has to be a same eigenvalue. If there has to be a same eigenvalue, then either it would be 0 or it could be 2. It cannot be 0, that's why it has to be 2. So value of alpha is 2. Rest all the values I already know. Get the answer. Understandable? So it was a good question. Let's go to the next one. A is a 5 cross 5 matrix and eigenvalues are mentioned. So which of them are true? Which of the following types of matrix A can possibly be? What is the meaning of skew symmetric matrix? Here eigenvalues will be imaginary or 0. So eigenvalues are imaginary or zero. Yes, it is possible. Same for skew Hermitian matrix as well. Eigenvalues will be either imaginary or zero. Yes, this is also true. What about orthogonal? For orthogonal matrix, determinant has to be 1. Sorry, not determinant has to be 1. Sorry guys, I should say the magnitude of eigenvalue has to be 1. What is the magnitude here? Magnitude is 2. What is the magnitude here? Magnitude is 2. What is the magnitude here? 6. Here magnitude is 6. Here magnitude is 0. That means it is not true. For real symmetric matrix, eigenvalue has to be real only, which is also not true. Okay, so only A and B are true. Understandable? Now for the next one, which of the following can be the eigenvalue of a orthogonal matrix? What is the condition? That determinant, not determinant, the magnitude of eigenvalue has to be 1. What is the magnitude here? Magnitude is 1 only. So yes, that is correct. What is the magnitude here? 2 plus I divided by under root 5. So what is the magnitude of 2 plus I? 2 plus iota, that is 2 square plus 1 square, and then take the under root. So magnitude is under root 5 divided by under root 5. That is equals to 1 only. So this is also correct. What is the magnitude here? 3 and 4. 3 square plus 4 square, that would be 25. So under root 25 divided by 5, that is also equals to 1. So this is also the value. What about this one? 7 and 3. 49 plus 9. 7 square will be 49. 3 square will be 9. So this will become under root 58 divided by 6, which is not equivalent to 1. So this is not true. So eigenvalue of a orthogonal matrix means the determinant, sorry, not determinant, again and again I am saying determinant. The magnitude of eigenvalue should be 1. So yes, this could be possible one of the eigenvalue, this could also be possible one of the eigenvalue, and this could also be possible one of the eigenvalue. Okay, the magnitude has to be 1. Understandable? This is a gate question. In my attempt it came, gate 122. So last question you need to attempt it, last question of linear algebra. Okay, attempt it and get the answer. No matter whichever the way you use, this was the question, you need to get the answer. So let's use the method 1. In method 1 we are going to use the mathematics, not any matrix. Okay, simply we are using the mathematics. What is given? Matrix A is given as alpha v1 v1 transpose beta v2 v2 transpose. So if I have done the proof in a good manner, then what I can think? I know that I need to find out the eigenvalues. That means Ax equals to lambda x. This is something I need to prove. This is something I need to get. If I multiply this matrix A, if I do the post multiplication by v1, what I will get? Sir, alpha into v1, v1 transpose into v1 plus beta into v2, v2 transpose into v1. What do I see here? What do I see? v2 transpose into v1. v2 transpose into v1 will be 0. If v1 transpose into v2 is 0, if v1 transpose into v2 is 0, then take the transpose on both of the side, what you will get? v2 transpose into v1 should also be 0. Basically, if this is the scenario, that means v1 and v2 are orthogonal to each other. If they are orthogonal to each other, then this is also true. So this value will be 0. And what about this value? v1 transpose into v1. v1 transpose into v1, that is 1. This value is 1. So what you are getting? A into v1 is coming out to be alpha into v1. This is what you are getting. What does that mean? A into v1 is coming out to be alpha into v1. That means eigenvalue is, one of the eigenvalue is alpha with eigenvector v1. One of the eigenvalue is alpha with eigenvector v1. Similar thing I can do with A dot v2 as well. What I can do? A dot v2 also I can do. So alpha into v1 transpose dot v2 plus beta into v2 into v2 transpose dot v2. Understandable? What this will be? v2 transpose into v2, that would be 1, and v1 transpose into v2 will be 0. So A into v2 is coming out to be alpha is gone, and this will become beta v2. What does that mean? One of the eigenvalue is beta with eigenvector v2. Understandable? Okay. So two eigenvalues I have find out, alpha and beta. Is there any option? Alpha, beta. Alpha plus beta wrong. This is wrong. This is wrong. So I will click on this one. But how, sir? How you can say that 0 is also one of the eigenvalue? How you can say so? 0 is also one of the eigenvalue. That if I need to prove. So what I will say? Sir, A is given as alpha into v1 transpose v2 transpose, v1 transpose plus beta v2 transpose. If I take the trace on both of the sides, trace of A, what that would be equivalent to? So trace of alpha into trace of V1 transpose plus beta into trace of V2 transpose. How I am able to write it down? How I am writing it down? Trace of alpha into A plus beta into B is equivalent to alpha into trace of A plus beta into trace of B. Do you remember this thing? So similarly, alpha you take outside, trace of V1 into V1 transpose plus beta into trace of V2 into V2 transpose. So trace of A is coming out to be alpha. What is the meaning of this? Trace of V1 into V1 transpose. What does trace of V1 into V1 transpose represent? This represents the length of V1 whole square. So it is nothing but length of V1 whole square plus beta into length of V2 whole square. Now what is length of V1 and V2? From here can you comment what is the length of V1 and V2? I can simply comment that sir, length of V1 and V2 both are equivalent to 1 only. Both are equivalent to 1. From these expression I can comment no. V1 transpose into V1, what does this represent? Length of V1 square. These things we have seen and again. And what V1 into V1 transpose, trace of that would represent? That would also represent the length of V1 vector. So this is what we are doing. And length of V1 vector I can understand that it is 1, it is also 1. So what we are getting, the trace of A is coming out to be alpha plus beta. So what do we know? Eigenvalue of A is something I don't know, alpha and beta, and trace of A is alpha plus beta. And let's just say this eigenvalue was lambda 1. So I know that addition of eigenvalues will always be equal to the trace. So what is the lambda 1 value we are getting? That is 0. So what does that mean? What all are the eigenvalues? Eigenvalues of A are 0, alpha and beta. Will you be able to think this much in the examination hall? That's a major concern. Will you be able to think 0, alpha, beta in that manner? At least this much you can think, no? That if you are able to get alpha only, then it will be done. Right? They did not want to make it too tough. If they wanted to make it too tough, they could have asked anything, that what will be the eigenvalue and tell the corresponding eigenvector, all these things they could have asked. Right? They could have simply mentioned here the length. Why they would do V1 transpose into V1? They would have simply mentioned that length of V1 equals to length of V2 equals to 1. This they could have mentioned. But they made it very simple, that even if you are able to think this much, then also your job is done. Just simply multiplying with the V1. If you just think this, if you just think about this one, and then just think that simply multiplying with V1, your job would be done. Why is that so? Because here I will multiply with V1, this will become 0, this will become 0, this will become 1, and this is the condition I will be getting. That means eigenvalue will be alpha, eigenvector will be V1. So only one of the option is having eigenvalue alpha, and none other option is having eigenvalue alpha. That means I will be able to cut these options and I will get my answer. Okay. But other way are also there, no? What could be the other way? If I see all those things written in the examination, which things written? If I see this thing written, V1 transpose into V2, what I will say? First thing, V1 transpose into V2 is written equals to 0. What I will say? From here I can say that V1 and V2 are orthogonal to each other. This is the first thing I can conclude. If these things are written, then I will be able to comment that their length is 1. Right? Their length is 1 and they are orthogonal to each other as well. So can I assume any eigenvectors like that? Not eigenvectors, can I assume any column vector like that? I need to frame a column vector, right, which are orthogonal to each other having length 1. 1, 0, 0. V2, 0, 1, 0. Are they orthogonal to each other? V1 is orthogonal to V2. Are their length is also 1? Yes sir, their length is also 1. Job done. If I am able to assume this one, can I write down the value of alpha into what is A? Alpha into V1 into V1 transpose. So at the end of the day, I will have to calculate V1 into V1 transpose, no? So let's calculate V1 into V1 transpose. What I will be getting? V1 is 1, 0, 0 and V1 transpose is 1, 0, 0. What I will get? 1 into 1, then 0, then 0. Then 0 here, then 0 here, and then 0 here. Then 0 here, then 0 here, and then 0 here. This is what we are getting. And what about V2 into V2 transpose? 0 1 0 0 1 0. 0 0 multiply with 0, then 0 multiply with 1, then 0 multiply with 0, then 1 multiply with 0, then 1 multiply with 1, and then in the end 0 0 0. This multiplication you can do on your own. So this is the scenario we are getting. Now what is our matrix A? Matrix A is given as nothing but alpha into V1 into V1 transpose plus beta into V2 into V2 transpose. So multiply this matrix. This is nothing but V1 into V1 transpose, no? And this is nothing but V2 into V2 transpose. So multiply this matrix with beta. What you will get? Here you will get beta. And multiply this matrix with alpha. Here you will get alpha. Then add both of them. What matrix you will be getting? So this kind of matrix I will be getting. Multiply this matrix with alpha. So alpha 0 0 0 0. Right? Alpha 0 0 0 0. Then everything 0. And here 0 0 0 0 0 0 multiply with beta. So this matrix I will get. What kind of matrix it is? It is a diagonal matrix. What are the eigenvalues? What all are the eigenvalues? So here, sir, eigenvalues are coming out to be alpha, beta, and 0. These are the eigenvalues that we are getting. Alpha, beta, and 0. Alpha, beta, and 0. Okay. So this is how, if I am able to think of the matrix, then I will be able to get the answer. This question came in my examination hall. Very interesting thing I am telling. So this came in my examination hall. I don't know, at that time I was not having this kind of concept, right? Because there was no PrepFusion at that time. Okay. So I was not having good enough concept. Okay. And then I just assumed very complex matrix, not this simple matrix. This is a very simple matrix. No? So I assumed a very complex matrix satisfying these conditions. First I thought that A, B, C I will take. Satisfying these conditions, I assumed some complex matrix. Then I solved it and I got this answer, 0 alpha beta. I clicked on this. How much time I took to solve this question? More than 10 minutes. Why is that so? Because I took complex matrix. No? I took very complex matrix. V1 and V2 I took very complex. 1 by under root 2 minus 3 by under root 2, something like that. I took very complex matrix. And then I solved it. I got this answer. I clicked on 0 alpha beta. I took 10 minutes. It was fine. I did it all. Then I attempted other questions. I attempted my full question paper. So in my examination, roughly around 20 seconds were left. I was done with the examination. I dropped my pen. I would say that yes, 20 seconds are left. Then examination will get over and I will go home. Suddenly this question clicked to me that 0 alpha beta is the answer I am getting. I again came back to this question. I don't know what really came into my mind in the last 20 seconds. I removed this option and I clicked on this option. 0 0 under root alpha square plus beta square. I solved it completely. I was getting this answer as well. I spent more than 10 minutes. In the last 20 seconds, I don't know why I removed and clicked on this answer and I got minus 2.66. Okay, so I remember this one. So you do it all. You have marked this one as well. But always in the examination hall, if you feel like that in the last 20 or 30 seconds, if you feel like changing some answer, then don't do it. Never ever do it. Whatever your intuition says, ignore all your intuitions. Don't even look at the screen. Okay. So this is the message that I wanted to give. This has happened with me. Even in JEE examination, it has happened. Even in JEE, this thing has happened with me. So in the end, whatever the answer that I change, I was not very confident in 0 alpha beta. No, why I was not very confident? Because I took a very complex matrix. I took a very complex matrix. The matrix was very complex. So when I took very complex matrix, then I was not confident. Then I don't know what really clicked to me, what I thought at that time. I just changed the answer. And there you go. I got minus 2.66. Okay. So yeah, it happens. So this is a message, or this is kind of a motivation you can take, that never ever, in the end, never ever change your answers. Okay. Yeah. Thank you very much. Your linear algebra is completed. Now we are going to start calculus. The calculus we are going to start from 7th of May. From 7th of May, I will start uploading the videos of calculus. So linear algebra is completed. Sir, where are the notes? Notes will be there in our Telegram group. Notes will be there in our Telegram group. What will be the name I will keep? The name I will keep is linear algebra mathematics. Okay. Linear algebra engineering mathematics. This is the name I am going to give. Engineering maths. Okay. So you will get the printable notes as well, and you will get the slides as well. So printable notes means you can simply get the printout of it and you can study from there. Slides means you can annotate on the device or you can study from your PC. So both of the notes you will be getting, and in the similar manner I will keep on uploading the notes. In the similar manner I will keep on uploading the notes of other subjects as well. So today I will upload the notes, printable notes also I will do, and complete content is also done. Next we are going to start calculus, which is common for all the branches. Okay, so calculus we are going to start. Thank you very much. Happy learning. And you comment down how you felt about linear algebra. Please do comment down that what was the level of linear algebra, how did you feel. Thank you very much.